Welcome, welcome, welcome. I'm not going to waste your time. I'm going to go quite quickly, assuming you have some development knowledge. And these concepts are going to be fundamental to understanding how HTTP works and how you can self-sign your own certificate to run HTTPS in a localhost environment. I want you to understand it fundamentally. It's only going to help you in the future. Without further ado, let's begin. Let's start with HTTP. How does that work in a traditional sense? Well, let's say you navigate to a browser and you want to log into your bank, right? So you navigate to bank.com, and on here there's a form that you fill in, a login form where you type a username and password. Now, fundamentally, everything sent over the wire has to be converted into ones and zeros. So although you will be seeing a string at some point, and this is the format of a form sent over the wire using a post HTTP request, but it has to be converted into binary. Why? Well, just remember, everything sent over the wire is electrical inputs, either on or off. And the easiest way for us to visualize that, of course, is binary zeros and ones. So those have to be sent over the wire in order to reach the other side. Okay, but here is the problem, my dear student. We've got this username of Wally and a password of secret. We type that onto this form in our browser. As soon as we hit send, we know it's going to be converted into binary and it's going to be sent over the wire to the server. But I don't like my name and password being sent over the wire that everyone can see. Let me explain. So we know, okay, that you probably have a router at home. So there's going to be a router, and that router will be the one with the public IP address interacting with the World Wide Web. The router will then send this post request to the server. Which server am I talking about? Well, this is going to be bank.com server. And remember, the bank.com server, it's going to receive the same binary sent by the browser. And it's very easy to convert binary into text. You just use encodings. And of course, the server knows then your username and password. It can verify that on the database, etc., etc. Okay, so where's the problem, Clyde? Well, this is the problem with HTTP, is that transporting data like this is not safe. That's the problem with HTTP. So for example, there could be a man in the middle who wants to intercept and view this data being sent on a network. And it's very, very easy. For example, you can just buy a product, and let me just move the browser here. You can use a product like this and many others to demodulate Wi-Fi signals into binary. So it's very easy for a man in the middle to listen to this transaction here. So what I mean is that this data being transferred over the wire, it could be hacked, okay? A bad man, a bad person could be listening to this. What does that mean? Well, of course, it means that they will have access to this binary. Of course, because they have the same binary, ding, 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 you already know that they'll be able to encode that into text. And they'll be able to view your username and password. Whew, so there you have it. I mean, it's obvious. You probably knew all of this already, and that's fine. In the next lecture, I just want to open up a local server, and I want to show you this in action. I want to use Wireshark to analyze the packets. I want to show you that really, when it comes to HTTP, nothing is encrypted. So buckle up, and I'll see you in the next lecture. As promised, I want to show you this HTTP in action. And I've got a very simple file here. I'm almost even embarrassed to walk through it with you because it really is simple. It's only going to prove the point that HTTP is not encrypted. So I've got inline CSS styling here just to spaz it up a little. And I know inline styling is terrible. I then have a little bit of JavaScript where once the user submits the form, there's just an alert form submitted. And then I don't want to prevent the default browser refresh, okay? Because I actually want it submitted over the wire and I want to capture that submission using Wireshark. And then of course, I've just got a body tag and this forms, our HTML. And I've just got a form and within that, the username and password. Pretty stock standard. All right, well, what I want to do, and let me just remove myself so you can see here. I want to click on this Go Live button. Can you see it? That's just Live Server, which is very easily installed in Visual Studio Code. It just allows you to use a local development server to serve files. Now, let me be clear, you do not have to use Live Server. In fact, we could just use Localhost. Localhost is your own machine, and you can use your own machine to host websites, but you need software so it understands how to deal with HTTP. So you have to, at some point, use some kind of software, like Apache. If you've got XAMPP installed, for example, you can use Node, or we can use Live Server, which is what I'm doing here. Okay, what do I want to show you? Well, firstly, if we go to the dev console, and I'm just going to hit Control-Shift-I, you can right-click and also go inspect, that's fine. And I want to go to this network tab and just hit refresh, Control-R, and we can see here there's only one document, this index.html file. And if we click on that, firstly, we can see this is using HTTP. That's the protocol being used. And here's our IP address, 127.0.0.1, aka localhost. We are running on port 5500 in this case. You can see the response from the server is this entire HTML doc with all of our JavaScript. Don't worry about this WebSocket section. That's injected automatically by live server. Effectively, what that's doing is it's allowing the page to refresh automatically every time we make changes to our file. So you can just ignore that. But here's our entire response. Nothing is encrypted, and I can prove it to you. So what I want to do is I want to now open Wireshark. It is free. You can go to the website, download it, and you can start analyzing traffic. It really is useful. And what I want to do here, I'm just going to click on this adapter for loopback traffic capture tab. This just allows us to listen for localhost activity. So I'm going to double click on that. And I want to now go to our browser and I want to refresh. So I've refreshed. Let's go to Wireshark. We can stop recording now. And this is what I want to show you. Here we can see our HTTP. Don't worry about the TCP, SYN, SYNAC, ACK. That just establishes a connection. We are interested in this HTTP. There's our GET request that we send to the server. But I'm interested in the response. And I can see here we've got a not modified response. So what's actually happened here is I can't show you the actual HTML. Why? Well, because it's been cached and the content hasn't been modified since our last visit to the page. I actually want to show you this. So you know what I'm going to do? Let me just restart listening. Let's go to the browser. What I want to do is I want to empty cache and implement a hard reload. I just want to hold down the mouse button on this refresh button and then empty cache and hard reload. Now let's go to Wireshark, stop recording. Now when we look at the HTTP response from the server, we actually see the entire response. So I can click on this response and would you look at this? Would you look at this? We can actually see the HTTP headers all in here, which is really, really nice. Here's the binary that's sent on the right. It can be encoded back into English words, which is why we can actually read it on the right here. But what's interesting, and Wireshark is quite nice like this, they dissect the actual response for us. So here it is here. If I click on that, we can actually read the response. There it is in binary, but here's all of our CSS. If we scroll down, there's our JavaScript function. Here's our actual form, our HTML. This is the point I'm trying to make. It's not encrypted. It's not a good thing. Okay. Now, I want to do something even more brave. What I want to do, and let's just restart this capture here. What I want to do is I want to now submit our information. I want to type Wally, and Wally can have a password of secret. It's no secret. All right, and now I want to hit submit. Are you ready? Okay, I'm going to hit submit. We get our alert, we click OK. Don't worry about the error on the page. I haven't implemented any server-side code to deal with the post request. But look at this. Let's go to our network tab, click on our post request here. Of course, there's no response, but let's look at the headers. Okay, we know it's a post request. We know it's being done over HTTP. And if we inspect the payload, we can view it here. Username Wally, password secret. This is just what you saw in the previous lecture. I might be thinking, Clyde, this is fine. It's only in our browser. Once it's being sent and transmitted over the wire, surely it's encrypted. No, it's not. And we can go to Wireshark. Remember, we have been recording, so I can stop the recording now. And, when dealing with Wireshark, you'll soon notice there are so many packets being captured here. We've got that WebSocket from live server being run in the background, which is why we're seeing all of this. So we can implement filters. One of the filters I can do here is we know we've submitted a post request. Why do I know that? Well, if we go to our file here, I've specified that this is a post request on our form, okay? Let's go back to Wireshark, and I just want to implement a very simple filter. I want our HTTP request method to be equal to post. And if I filter by that, it should reduce this considerably. But here we go. Here's our actual post request in Wireshark. And remember, people can intercept this. So I can hit on this post request and we can start examining it. Again, Wireshark makes it very clear that we have access to our Wally and our password secret. It's not encrypted. It's not hidden. It's being sent as is, as plain text. Have you got it? This is important. But let's move on. I want to quickly compare this to HTTPS. I want to show you that with HTTPS, things are not as trivial. We can't view things like this. In fact, everything is encrypted. So take a break and I'll see you in the next lecture. Welcome back. And now I want to quickly look at HTTPS, and what better website than Google itself. So I'm just going to navigate to google.com here. Firstly, you'll notice if we click on this URL section here that our connection is secure. And I'm going to be getting into this a bit later in the course because we can look at their certificate. Now, in order to run your website over HTTPS, you have to have a certificate. What is a certificate, Clyde? Don't worry, I'm going to be getting into that soon. This is what we need, by the way, even if we are wanting to convert our local host to run over HTTPS. It's part of the protocol, okay? So we need the certificate. But what do I want to show you quickly in this lecture? All right, well, I'm going to go to the network tab once again. You should know the drill. And let's just refresh, then it will capture everything. And you'll notice if we click on this all button, there's a lot of things happening here. So what you might want to do is just filter this to look at documents. I only want to look at this HTTP request for the index page, okay? And if I click on that, well, firstly, before I even click on that, can you see the protocol is H3? That means we're using HTTP3 here, which is implemented using UDP and Quick. But anyway, if we click on that, you can see here it is HTTPS, and it is being run on port 443. That's the default port allocated for all HTTPS traffic. All is good and well, Clyde. But if I click on this response, well, when I look at this, I can read their JavaScript functions here. I can read everything sent to us over the wire. Here's all the HTML for this page we're seeing right in front of us. The question is, well, how's that possible? I thought it was encrypted. Well, it is encrypted for everyone else in the middle, but it's not encrypted for us, and it's not encrypted for actual Google server because they can decrypt it. But if we try and intercept this in the middle, if we try and look at this, for example, through Wireshark, we won't be able to do what we did with HTTP 1.1. We won't be able to see this. It'll all be encrypted. So let me prove that to you. Let's just go to Wireshark quickly. And I know previously we were looking at localhost, so we were on this tab, adapter for loopback traffic. But now I want to look at, or examine packets on my Wi-Fi here at home. So I'm going to click on Wi-Fi. I then want to navigate to Google and just refresh the page. If I now go back to Wireshark, we can stop recording. This is what I want to show you. Can you see any HTTP here? Any HTTP request and response? The answer is no, we cannot. It's all this quick. You can see here it's got protected payloads. If I try and open up any payload, it's just a random bunch of gibberish. So right now, there's no way for us to examine HTTP3 packets. Well, there is actually a way. I can access the session keys that are exchanged between our browser and server. And I'll do that later in the course. I'll show you how we can examine, but you can only do so on our own machine because we have access to those session keys. Okay, but I'll get into that a bit later. By the way, you might be thinking, Clyde, this is capturing so many different packets, not necessarily just from us in Google. So what you can do, you can go to the network tab, which we were on before, and here's the IP address. Now, this is, of course, not IP version 4, this is IP version 6. So we can filter all those packets to only look for those related to this IP address. So I can literally just highlight this, copy it. We can go to Wireshark, and we can apply a filter. The filter here will be IP version 6 address, and I'm just going to paste it in here. There we go. So now we're filtering everything that has been exchanged between our browser and Google server. Okay. Whew, I know, quite a lot. Now, the question you probably have is, Clyde, okay, I get it. It's all encrypted. I can't read anything here. It's just gibberish. How does our browser know to read it? How does our browser know how to decrypt this text? That is a good question. And in order to understand that answer, you have to understand encryption. So let's now dive into encryption. Buckle up, stay motivated, and I'll see you in the next lecture. We have a user called Wally who typed in a password of secret. The question is, how do we send that over the wire? Well, you guessed it. We have to encrypt it, okay? And let's say we want to send it to a lovely lady. How do we do it? Firstly, I just want to get terminology correct. The actual secret itself, that is referred to as plain text. When we encrypt it, whatever that resulting value will be, that's referred to as ciphertext. Now, I don't want to get complicated yet. I just want you to understand, well, let's use a very simple encryption algorithm where we take our letters and we scramble them. Pretty straightforward. Now, having such a simple algo sounds great in theory, but it does pose problems. Let's say you also want to send the same plain text secret to another user. And let's assume we're using the same algorithm, therefore it will result in the same ciphertext. Now, what's the problem with this? Can you see? We've got two parties now that will have to know the algo in order to decrypt that ciphertext back to the original plain text. So once any one of these users know that algo, well, they can steal information from the other user. And although these two individuals here look quite honest, that may not always be the case. You may have a horrible thief part of this picture. So here we have a form of encryption. It's just not very secure. It's not very good. How could we improve on it? Well, obviously you might be thinking, Clyde, let's not produce the same result every time. And yeah, you're kind of getting there. So you could argue, hey, let's have a new algo produce a new ciphertext result on every iteration. And this is a possibility. However, think about it practically. Producing a new algorithm every single time you want to send data, well, it's just not practical. It's not scalable. You'll have to find a way to scramble text differently for every single transaction. And remember, the algos cannot be seen by anyone else or figured out by anyone else. So, what do? How do we yet improve on this approach? That's a great question. And the answer is we use key-based algorithms. Keys are great because you're using the same algorithms, but you kind of randomize them with a key. A key is just a string of random text, ultimately ones and zeros. So here we go. You know the drill. The difference with key-based encryption is that the algorithm itself is consistent across all instances of sending data, which is quite useful. However, like I just mentioned, there is a random key generated for every single transaction, which makes the ciphertext unique. And this achieves our results. Every user gets a random encrypted string. Okay, well, we're done. Not so fast. It's not as simple as this. There's not just one key. I know, just to complicate things. So let's take a break here. In the next lecture, I'm going to teach you about the 2 ways that you can encrypt data using keys. It's going to be quite interesting, and it's so practical because it's used today. All right, I'll see you in the next lecture. As I mentioned in the previous lecture, there are 2 ways to implement key encryption. Do you know what they are? Well, the one is symmetric encryption. Symmetric, what does that mean? It just means the same. So therefore, the same key will be used to encrypt the plain text and to decrypt the data back into its plain text format. Same key. What's the other type of encryption? That's right, asymmetric. And I'm sure you've already guessed it. These have 2 keys. One key is used to encrypt the plain text message and the other one is used to decrypt it. Now, it doesn't matter which key does what. As you'll see later in this course, when it comes to HTTPS and TLS, the industry refers to the one key as a public key and the other one as a private key. One is used to encrypt, the other one to decrypt. Now, I want to show you an example because this is just mumble jumble. And in order to do so, I just want to have a base of data. Now, pretty much most algorithms have to have some sort of base data set or mathematical construct to perform their functions, their algorithms. For example, a very common one when it comes to HTTPS is the RSA algorithm that relies on the prime number data set. You've got the ECC algorithm, which relies on elliptic curves. You've got AES, which is very common, that relies on blocks of text. Actually, it's the plain text. If plain text is very large, the AES algorithm reduces it into smaller blocks, and it works on those blocks. My point is every algorithm needs some sort of base data set. So in our example, why don't we use the alphabet as our base data set for our algo? I'm keeping it simple. All right. Next, I don't want to look at asymmetric first. So let's just move that out the way. And let's just look at this symmetric key generation and encryption method. How would we go about doing this? Well, let's say that our algorithm just takes our plain text and the private key's value will specify how many letters in the alphabet forward do we go to produce the ciphertext. Okay. So for example, we've got our plain text secret. Next, let's use our custom algo to produce a private key anywhere between the values of 0 and 26, right? The number of letters in the alphabet. Let's say our private key here is 4. So getting back to our alphabet, what does this mean? Well, let's work on every single letter in our plain text secret. The first letter is S. Go to S in the alphabet. What's our private key? 4. So we go 4 letters forward. There we go. And we get to W. So then we know that our very first letter is W of our ciphertext. You with me so far? Of course, we can continue this. The next letter we know is E. We start with E. We go 4 forward. What do we get? That's right, we get I, and we can continue this whole process, and we get to the ciphertext here. Pretty straightforward. Okay, Clyde, I kind of get it. Now let's say the user on the other end has the ciphertext. How do they get back to the original plain text? Well, firstly, we're using the same private key, which is also the value of 4. But now, when it comes to symmetric keys, we can reverse the algo. We can work backwards. So it's very simple. We've got our alphabet here. Now, we start with the letter W. Where's the letter W? There it is. And notice this. We can go backwards. This is so important because you cannot do this with asymmetric key generation algorithms. They are one-way functions, as you're going to see. So we go back 4. 1, 2, 3, 4, and we get to S. Of course, this means this first letter is going to be S. We do the rest, same logic, and we get to secret. This is the basis of symmetric key algorithms, and it's so useful. Why is this useful? Well, it's very quick, but it does come with its downsides, and that's why when you first establish an HTTPS connection, you cannot use symmetric key algorithms initially. As you're going to be seeing, eventually we want to get here. Once the client and server have established a secure connection, they can actually exchange these private keys to each other that are very unique to that session, and they can encrypt it kind of like in this way. It's quite interesting. But anyway, there's a process involved in order to get there, and I will be touching on that more in the course later. For now, this is symmetric key generation. Okay. Makes sense. But Clyde, teach me about this asymmetric encryption. How does that work? Well, okay, and I'll go faster here. Firstly, we're in the same situation, right? We want to convert our secret into ciphertext. We produce an encryption key, and let's set that to 4. Same as last time, so we get the same result. Right, you know the drill. I'll go here because of our key. We have to go forward 4 letters every time. This is all good and well, but how do we now decrypt? Well, you guessed it, we need a decryption key, another key, and this time it's 22. But bear in mind that, remember what I said previously, an asymmetric key is a one-way or trapdoor function. Okay, they do not allow you to reverse engineer the function. So we can't go backwards, we have to keep going forwards. So here, the value is 22. Now something very interesting is that it does relate to the first key. Both keys have to be mathematically related. In fact, we know we're dealing with an alphabet, so the sum of the two key numbers has to always be 26. So let me show you how this would kind of work. Let's get back to our alphabet here. Remember, we don't have the secret yet. Okay, that's what we're trying to decrypt back into. So we're starting with the letter W. We find letter W here, and our decryption key is telling us, hey, we've got to move forward 22 letters. So here are the 3 letters here, and then the remaining 19 letters are here, and of course we get to the letter S. That's the first value of our plain text word secret. If you continue this process for each letter, we get to secret. This is so important for you to understand. For now, just realize that these keys can be switched around and it'll work just the same. So for example, this key we can use to decrypt, and this decryption key value of 22 we can use to encrypt. Doesn't that just blow your mind? And it'll work just the same. So this is now our decryption key, and this is our encryption key. It'll work. I won't go through the math with you, but if we start with S, we start with S, and now if we move forward 22 letters, we get to the letter O. So the first letter here, or O, and if you continue the process, you're going to get to this ciphertext here. By the way, you are going to get different ciphertext, but it'll work. Of course, the same logic will apply when you decrypt. Remember, we have to go forward. But of course, here we're starting with a value of this the ciphertext here. I'll just do one letter with you. Start with O, and we move forward 4 letters. 1, 2, 3, 4, and we get to S, which is the first letter of our secret. Okay, continue it, and Bob's your uncle, we're done. Well done. I know this is pretty heavy. I'm going quite fast. What is the conclusion of all this? Well, there you go. It's on the screen. Okay, I think just realize that the information you're learning here is very real. With HTTPS, one key is labeled a public key, another key is labeled a private key. The private key is never shared over the wire. The browser will always keep its private key private. The server will keep its private key private. But either side can share their public keys with each other, knowing that the only way to decrypt the data is with their own respective private keys. I've already spoken about symmetric keys being a lot faster. They use less bits when it comes to key generation. Asymmetric, on the other hand, I'm sure you've guessed it, is a lot more computationally heavy. It takes more processing power. You've got to send more bytes over the wire. So it also comes with cons. However, with TLS, with HTTPS, the truth is a combination is used. Now, don't worry if some of these concepts are still a bit fuzzy and exactly how the keys are exchanged. I am going to be delving into that very soon. I just wanted you to understand in this lecture what encryption is and the 2 types of encryption. You can use the same key to encrypt and decrypt, or you can use different keys. Different keys is a lot more secure, but it's a lot harder to calculate. And today, the truth is, we use both. So I think this is a good place to stop. You know what I want to show you? Do you remember, of course you'll remember, a few lectures back, we looked at HTTP 3 when it came to just visiting google.com, and we couldn't see anything, right? Let me ask you this question. If we have the key, a key of some sort, would we be able to decrypt that information in Wireshark? Yes, we would. And do we have the key? Yes, because we know that our browser is making a request to google.com, it's receiving information, and it's decrypting it and displaying it to us on the page. So therefore, our operating system, our PC, has to some way store these keys. So in the next lecture, I'm actually going to show you how we can grab those keys, put them into Wireshark, and then I just want to show you that we can see the underlying decrypted HTTP 3 text in Wireshark. Super exciting. See you in the next lecture. Welcome back. And like I mentioned, what I want to do now is I want to navigate again to google.com, but I want to show you how to capture the session keys. Now, these session keys are generally done using symmetric key encryption, but this is not done initially. When a TLS connection is established, certain pre-master keys and secrets are exchanged, and in order to exchange those keys and those secrets so that both sides have the same symmetric key, we have to go through asymmetric key encryption, okay? Perhaps that's a bit too much detail that I need to share, but that's what happens. Now, I want to open up Wireshark, which is what you see here. I want to now navigate to I'm opening up our browser, and I want to navigate to google.com. We know the drill. All right, let's go to Wireshark. Let's stop recording. Now I know there's a lot of activity going on here. I've got other software running in the background that's using Wi-Fi. So I want to filter just for google.com. Now I did show you that we could go to the network tab and copy the IP address, but there are many ways to do the same thing in coding. So I'm just going to open up Windows command prompt. This is the original command prompt on a Windows operating system. And I'm just going to use the ping command, and I'm going to ping google.com. That's simple. And there you go. You can see we've got the IP address. Here it's using IP version 6. So I'm just going to copy that. And now, of course, we can filter. IP address. Oh, no, it's IP6, right? IP6 address. And there we go. All right. And, this is very, very interesting what you're seeing on the screen behind you or behind me. Firstly, notice that we are seeing Quick. Quick is built on top of UDP. So if we look at this very first data packet, which is our client sending an initial Quick packet to the google.com server. That's what that is. This is an initial packet. The size of the packet, you'll notice here, firstly, well, actually, before I get onto that, the point I was trying to make is that Quick is built on top of UDP, and we can see that here in this bottom left box. we can see that here's the UDP protocol, and on top of that, we've got this quick protocol. That's the first point I wanted to just draw your attention to. Next, I just want you to start feeling comfortable but with HTTP3, because HTTP3, well, more and more websites are using HTTP3, so you're going to need to know about it. The other thing I want you to just bear in mind here is that the size is quite large. It's 1,292 bytes. It's much larger than TCP. TCP has a three-way handshake, and those packets are generally quite small, like 70 bytes, a lot smaller than this. The reason is there's a lot happening inside this initial packet. Remember, with Quick, we don't have to go through that whole three-way handshake. It's much quicker. Okay, so let's examine this initial packet. We can open it up here, and bear in mind, I have not captured any session keys. I'm not using any session keys. So this is information that anyone can see, all right? But I just kind of wanted to get you familiar with what's going on here. Firstly, you'll see that we're on version 1 of Quick. This was standardized in RFC 9000 sometime in 2021. And this version 1 is, you know, the most recent stable version. There is version 2 currently in draft form. So you'll be seeing that shortly. But anyway, this is version 1 of Quick. And then you'll see here the word crypto. You'll see that also in the information here in Wireshark. Crypto is just indicating to us that cryptographic information, aka secure TLS kind of related information, is being transferred and negotiated between client and server in this packet, right? So we can open up this crypto tab, and here's some more information. Firstly, we can see that TLS version 1.3 is being used. We know that because we're using HTTP3. And here's the client hello. Here's the handshake protocol being implemented in practice. Very, very interesting. Secondly, you'll notice that our initial Quick packets are split into two packets. Packet number 1, packet number 2. And, you know, Wireshark is kind enough to provide us with links to the reassembled handshake message. So you can click on that. And we can look more into this handshake, right? Here's our TLS handshake. We can open it up. Here's the client hello. Very, very interesting. These are all the things you should be familiar with if you know TLS. And I know I don't have to be going through this with you, but I want you to become a grandmaster. I want you to start being comfortable with all these things. What else is quite interesting here? Under this application layer protocol negotiation tab, we can see what protocols being used. Here, it's the H3, HTTP3 protocol. The server name extension is quite interesting. It just you know, it's another security check just that we are navigating to google.com. It's just interesting. We've got the supported version of TLS 1.3. Sometimes you'll notice Wireshark shows this TLS version 1.2 is being used. I believe that was, you know, they did that for a specific reason to try and kind of fool software in certain situations. So don't worry about that. We are using TLS 1.3. And that's the client hello, right? Then, just out of interest, you can view the server response as well. Here it is here. Here's the server response. You know what? There's something else I want to show you. If we look at this initial packet sent from the client to the server, this destination ID, it's quite interesting. The browser is telling the server what ID it should have and vice versa. Okay, and this is a very unique ID. It's a very long string. And this is very unique to UDP and Quick, because what's happening is that you are assigning a session ID over Quick. So what does that mean, Clyde? Well, it means that if the underlying IP addresses change between the server and the client, it doesn't matter. You can still continue with the same session. So just, you know, practically, if you have a Wi-Fi connection in your home, you're watching a YouTube video, you then walk out to your car, and you now suddenly switch to another IP address, well, you can continue watching exactly where you left off. The same session can be used. That's quite unique. Anyway, okay, let's look at the server response quickly. We can click on the first response. And just out of interest here as well, can you see that inside the server response, there's an ACK here. And this acknowledgement number is 1. So therefore, Quick is reliable. Remember with TCP, we've got all the SYN and SYNACs and all those numbers. Well, it's kind of the same here. The server's saying that I received your packet and I've acknowledged it, packet number 1. Therefore, you don't have to resend it. So anyone who tells you that HTTP3 is not reliable, well, they're just wrong, so long as Quick is being used. There might be other protocols that do not use Quick, but still utilize HTTP3. But anyway, okay, What else do I want to show you? Well, if we try and examine now this server response, this crypto information sent, there is a little bit of information we can see that the server has sent to the client. Okay, there is a bit. We can open up this crypto tab. We can look at its server hello, its handshake information sent, and here it is. We can see the cipher suite used. Now we know that this is HTTPS over TLS 1.3 because the cipher suite format is a bit different with TLS version 1.3. Cipher suite information like this does not include the original or initial asymmetric key encryption algorithm that's used to exchange keys. This is because the elliptic curve, Diffie-Hellman, ephemeral algorithms are being used for that initial exchange, and they just don't have to advertise it, okay? Now, here's the thing. Okay, let's get back to the topic. Oh, I just find these things so interesting. Okay, if you do not have now a session key, you won't be able to really read anything else. And you can see here that we can't even see HTTP3 traffic. And if you try and analyze any more information here, well, it's just going to be encrypted, okay? It's going to be gibberish. We won't be able to see anything else. We can't even see HTTP3 headers, right? If I go to the browser, and we go to the network tab here, let's just refresh this page. You see all these headers, these response headers? These are HTTP3 response headers. We cannot see it in Wireshark, okay? Because Wireshark doesn't know about these keys. We haven't given the key to Wireshark. So how do we extract a key, a session key? Firstly, I want you to bear in mind that these session keys are short-lived. They are only temporary to the session currently being activated by your browser and the server. Okay, so anyway, how do we log these keys? Very good question. In order to extract session keys, well, your browser has to allow it. Remember, your browser is the software that's running on your Mac or PC that's managing the connection between, itself, the browser, and the server. And your browser has to allow us to extract those session keys. Luckily, Chrome does, Firefox does. So I'm going to use Chrome here. And I want to tell Chrome that when we establish secure connections, I want them to dump all the session keys into a file. So the first thing I want to do is I want to create a folder on my desktop called session key logs. It's empty at the moment. Next, I want to navigate to our environment variables on our system. I want to manage environment variables, and I want to create a new environment variable. Now, Chrome, when it navigates to a secure web page, it will automatically look whether there's a variable name called SSL key log file. You have to write it just like that. If that is found, it will navigate to this location here that we're going to tell it now and insert all the session keys into that file. So I can just navigate to our directory here. I can just copy the location and I can insert it in here. And then we can call the file anything we want. I'm just going to call it logs.txt, a text file. I'm going to hit OK, hit OK, hit OK. All right, done and dusted. Now, of course, the next step is we need to navigate to Google again in order to capture those session keys. So I'm going to go to Wireshark. Let's start recording again. Just delete everything else. That's fine. Let's navigate to our browser. I'm just going to implement a empty cache and hard reload. Are you ready? Done. Done and dusted. All right, we can go to Wireshark. We can stop recording now. Oh, and if I go here to our session key logs, why is nothing? I know why nothing's displayed. I haven't restarted the browser. So what I actually need to do is close the browser. You know what? Let's just remove everything. Start recording again. Now it should work. Hopefully. Let's navigate to the browser again. Let's go to google.com. Now let's go to our session keys and we can see it here. How awesome is this? You can even open it up and look at this. Look at this. Look at all the keys generated in that one call. There's a lot happening, right? A lot happening. But here is our secret key. Come on, you got to smile. All right, we've got the keys. Now what we need to do, let me just go to Wireshark and stop recording. We need to tell Wireshark where to find those keys on our system. I guess we could apply the IP filter for Google again. IP version 6 address. So this is good. But how do I tell Wireshark that where those SSL keys are? Well, you just go Edit, Preferences, you expand this protocol section and you type TLS. Here it is, and I've already pointed it there. This is where I've currently directed it to. that folder on my desktop in the file called logs.txt. And when you do that, would you look at this? Would you look at this? We are now able to see HTTP3. Where is it? Where is it? No, the filter wasn't working properly, so now it is. I don't know why, I just had to hit return. Now to reduce all this other noise, why don't we just go into our filter here and we use the ampersands, and then I just want to filter for HTTP3 traffic, which is something we could not see without those logs. And what do I want to show you here? Well, why don't we look at those headers, right? And if you scroll down here, packet number 243, we can see here that this HTTP packet contains header information. So let's open it up. Let's see it. Here we go, HTTP3, and would you look at that? There's our 200 OK status response, and here are all our headers in readable format. How interesting. Now, Clyde, show me more. There's a slight nuance with Wireshark. This feature is relatively new. What do I mean? I just mean that Wireshark support for us analyzing HTTP traffic is still work in progress. And remember, HTTP3 works over streams. Streams can be bidirectional. Pieces of information can be sent in different streams. So practically, it's a little bit tricky to perhaps decode related information. And for that reason, this is just a long way to say that we cannot easily see, for example, the HTML loaded in Google. If we look at these data packets, it's got the word data here. That's why if I try and look in this data packet, I cannot see anything. It's still encrypted here, which is odd because I've just given them the session keys. But hey, right, I don't want to go down the rabbit hole as to why Wireshark can't do it. The point is we have access to HTTP3. I've just showed you that we could read the headers in plain text format. So well done. Don't lose sight of the bigger picture. The bigger picture is you now know that there are different ways to encrypt data. Today, the most popular is key-based algorithms. There's symmetric encryption and there's asymmetric encryption. HTTPS uses both. The session keys we've just used now to kind of partially decrypt HTTP3 messages, well, those session keys are symmetric. They're based on that AES algorithm. But the initial TLS handshake uses asymmetric encryption. Okay? Whew, we've covered a lot, but there's still a lot to go. See you in the next lecture. Before we move on to the next section, I just wanted you to be aware that there are many different algorithms that can be used. Now, you got to think about this, right? A browser has to have pre-installed algorithms available to it. In fact, as part of that TLS handshake, the browser advertises to the server all the different algorithms it can use in establishing a connection. Now, there is a library called OpenSSL. I'm going to be talking about this later when we generate self-signed certificates. But I just want to show you that there are lots of algorithms that OpenSSL supports. These browsers have to use libraries in order to manage and calculate keys. OpenSSL is one such library. But there are others, like Boring SSL, NSS, and others. Anyway, the point I'm trying to make is we can access OpenSSL, and it should be installed on your operating system. I think it's default for Linux systems and Mac. For Windows, you may have to install it, but I'll show you how to do that later. In order to access OpenSSL, you just type OpenSSL, and I want to list all the ciphers. So I can type ciphers like this, hit return, but that is very unuser-friendly. I can't really read that very well. So I'm going to clear the console, and then I'm going to type OpenSSL again. I want to display our ciphers, but now I want it to be in a verbose format. So I just do -v, I hit return. This is just a bit more user-friendly. Well, would you look at that? We have a whole lot of algos here that are used, right? I mean, it's even supporting SSL, which is old school and deprecated. We don't use that anymore. So when you hear developers talk about SSL, well, they are old school. They don't know what they're talking about, or they are indirectly referring to actually TLS. TLS is all the latest and best algos. And of course, TLS version 1.3 is the latest. That's used with HTTP3. And I think this was the algo we actually saw in the previous lecture, right? That was used between google.com and our browser. I did mention this before, but TLS 1.3 cipher suites, just their format is slightly different. You'll notice with TLS version 1.2 that the cipher suite also displays the algorithm used for that initial asymmetric key encryption. okay? The ECDHE, the elliptic curve algos, that's not displayed with TLS version 1.3 because those elliptic curve algos are used by default. I don't want you to get confused with these algos. Just remember that they serve multiple purposes. So for example, these algorithms that we're looking at, yes, they are used for encryption. Remember, encryption just makes a plain text into ciphertext, into gibberish, so it can be transferred securely over the wire. But these algos can do different things. For example, they can also generate the keys required in order to encrypt and decrypt the data. Okay, so I just wanted you to bear that in mind. Hope you're having a ton of fun. Let's get back into it. All right, I just wanted to kind of point you out to this, that there are a lot of algos. But yeah, I think you're ready. I think you're ready to finish off this section. Stay motivated. Let's start digging deeper into certificates. What do they mean? And the whole concept around public key infrastructure. I can't wait, and I'll see you in the next section. Welcome back. Welcome to this section. I hope you are amped. I hope you are excited, just as excited as I am, having put these all together. Now, you are going to be blown away, and it is going to get quite heavy. I'm just warning you. Let's get into it. Before we get into kind of more into encryption and keys and how they work, let me just explain a little bit about HTTPS. Just remember that we are forced to use TLS when we use HTTP 2 and HTTP 3. Now, strictly speaking, HTTP 2 in the specification does not require us to use TLS, but all browsers enforce it. Now, what does this mean? Does this mean that when we use TLS, that no one can intercept our data? No. Let me be clear. TLS does not stop anyone intercepting data, because once it's on the wire, it's free for all. Anyone, including myself, including you, can capture data being transferred over a network. I showed you that in section 1. And just understanding that fundamental concept is already putting you streets ahead of your competitors. I know it sounds simple, but you'll be surprised at how many of these basic principles are not understood by experienced developers. So let me explain. Let's say a user is filling out a form and wants to send data over a network. Once it hits that wire, anyone can intercept that data. And of course, HTTPS cannot prevent that from happening. So what does this mean? Well, let's think about it. What is TLS trying to achieve? What does it help us with? You might have already guessed it, and this is the most obvious, is it encrypts data. So it makes that data confidential, meaning if someone does intercept that data, it's just going to be gibberish. But TLS does more than this. Let's think about it. Once the data hits the server, yes, it's still confidential, but TLS aims to achieve other things. For example, TLS also wants to ensure that that gibberish has been unchanged. It hasn't been tampered with, in other words. And what's another goal? There's still potentially another problem here. Can you see it? Think about the fact, if your computer is speaking to a server, how do you know that that really is the server you are intending to speak to? When you visit google.com, how do you know that data you are sending is going to google.com? Well, that's the other goal of TLS. It's to provide authenticity, that the data or the person you're speaking with is the actual intended person. Are you with me so far? Okay. So let me sum up here. Here are the goals of TLS. Confidentiality, which I'm just meaning that data can only be understood by the client and server. So if someone else intercepts it, well, it's just gibberish. The other goal is to provide integrity. Basically, you want to ensure the data hasn't been messed with, and then finally, you want to make sure that you are talking to the intended entity. Okay, well, this sounds all very simple, but I'm just giving you a warning. It does get a little bit complex because different algorithms are used to achieve these different aspects. In the previous section, we discussed encryption. The most common form of encryption, especially with HTTPS, with TLS, is key-based encryption. And there are two types of key-based encryption. Do you remember what those are? That's right, we had symmetric encryption and asymmetric encryption that has different keys. Now in this section, I'm going to be digging deeper into these encryption algos, and I don't want you to miss very important points in this section. 1, let's look at symmetric encryption. We know this is when you have the same set of keys to encrypt data and to decrypt data. If we look at those TLS goals, which one of those 3 goals do you think symmetric encryption achieves? The most basic, of course, and I'm sure you've got it, is that it achieves encryption which makes your data confidential. Next, I want to look at the second form of key-based encryption, and that is asymmetric encryption. Now, this is quite heavy calculations, and for that reason, it's a lot slower than symmetric encryption. But what do you think asymmetric encryption achieves? Yeah, I know, you might be thinking, Clyde, this is easy. It also encrypts data. Therefore, it also achieves confidentiality, and you are right. But what's interesting is that asymmetric encryption can be used for more things than just confidentiality. Interesting. Firstly, it's used in HTTPS to exchange this concept of a pre-master secret. What? Clyde, what is this all about? Don't worry, I'm going to be explaining more about this later in a lot more detail, but just remember, eventually, where you want to get to is you want the server and the client to have symmetric keys, the same set of keys. Why? Well, I keep saying it's faster, but this begs the obvious problem. How does the server and client get the same symmetric keys securely without anyone stealing those keys? Well, the solution is this asymmetric encryption. So you use asymmetric encryption initially to allow both sides to share this pre-master secret. In fact, it's the client that sends the pre-master secret to the server. I will be explaining that more later. And then they use that pre-master secret to calculate the master secret, which is then used to calculate those keys. Okay, so you can also use asymmetric encryption there. And in terms of the actual TLS goals, it doesn't really speak to any one of those goals. But there is something else we can do with asymmetric encryption that does. And that is we can use asymmetric encryption to provide authenticity. And we do so by this concept known as signatures. Now, you're going to be learning in this course that a certificate authority is the one who actually gives a signature verifying that the person you think you're talking to is actually the person you're talking to. Whew. Just when you think we're done, we are not. We've also got hashing. Hashing provides integrity, and I'm going to be showing you examples of this shortly. And now you might be thinking, Clyde, this is great, and surely this is all we need. Well, if we're talking about a browser and a server, or a client and a server, just bear in mind I'm using browsers, but we live in the internet of things. So it's any device that wants to initiate a TLS connection, not just a browser. It could be your smart TV, a PlayStation, an Xbox, etc., etc. So this is my question to you. Is this enough? Having symmetric encryption, asymmetric encryption, hashing between the client and the server, only those two entities, is that enough? Well, spoiler alert, it's not enough. And this is why we have to have PKIs, public key infrastructure entities. This is where the certificate authority comes into the picture. And what does that do? Well, that takes that authenticity component outside of the realm just between client and server. In effect, it's going to tell us that the server is actually authentic. Now, I know you might be thinking this is a lot, and it is a lot. It is confusing. This is why many developers don't understand or appreciate how TLS sessions are created. And I'm sure you can appreciate that there are many different algorithms that are needed in order to achieve all of these things. And this is exactly why we have cipher suites. It's just a way for the client and the server to agree to all the algorithms that they will use to achieve the goals of TLS. That's all a cipher suite does. So for example, you'll often see cipher suites structured like this. And in the previous, in the first section, I even showed you an example of us looking at a cipher suite, but that was with TLS version 1.3, which doesn't include this first algo here, right? But this is a traditional TLS 1.2 cipher suite. This is the structure of it, and it may look daunting, but each one of those words or terms on there, they are telling us something about the algos. For example, the very first item there, well, that's the algo used to share those pre-master secrets. In other words, that elliptic curve algorithm is an asymmetric key exchange algorithm that allows both parties to retrieve a pre-master secret. Okay, once that's done, we've got this next RSA algorithm, and that's just used by the client and servers to prove authenticity. It's kind of used with the elliptic curve algo to create that pre-master secret, that seed value, which is used ultimately to generate those symmetric keys. Don't worry, I'm going to be explaining it later. The next set of algos here are used for symmetric key encryption. This is our ultimate goal. This is where we want to be between client and server. And then, as you'll see later, all the data sent from client to server is also hashed. That hashing is done to provide integrity. So that's what that last SHA is. That's just a hashing algorithm. Now I'm sure you can appreciate, my dear student, that there are a lot of interesting and complex topics here. Most developers don't understand it, and it's so important because in order for you to generate your own HTTPS sessions on localhost, for example, or whether you're using packages like NPM to do so, you need to understand what's happening behind the scenes. It's going to make you a stronger programmer. Trust me. The days of HTTP 1.1 are pretty old school. You're going to be dealing a lot with TLS and HTTPS as a successful developer. So you need to understand these concepts. So hey, what are you waiting for? Let me be your wingman. Let me help you become a grandmaster in HTTPS. Let's get cracking. Don't lose sight of TLS goals, confidentiality, integrity, and authenticity. I want to now discuss confidentiality. And this is perhaps the most easiest to understand. This is where we use encryption algorithms. And like I mentioned, the most common is key-based encryption algos. And we have two types, asymmetric and symmetric key encryption algorithms. Both of these require keys. You know this already. And when we encrypt data, we know that we are achieving confidentiality. Let's look at a very simple example. You open up a browser, you navigate to your piggybank.com website, and you want to log into your bank. Well, you've got to type username and password. You're wanting to send sensitive data to your piggybank.com server. One way we can encrypt the data is that we can use the server's public key to encrypt all of our data on the browser side before it leaves the browser, knowing that only the server's private key can decrypt it. So here we go. We've got a server, and every server, my dear student, operating over HTTPS, every server is going to have this public key and a private key. This public key, well, it is public. It's public for everyone. And I can prove it to you. Let's just navigate to google.com here. And if you click on this tab in the browser, we know that the connection is secure. You click on that and we can actually view a certificate. Now we're going to get into more detail later about the certificate. But for now, just realize that this certificate displays this public key. This is the public key of the server. And you can even click on details and we can look at another form of that public key. Here, subject's public key. Can you see it? This is it. It's public. Everyone has access to google.com's public key. But that private key, no one has access to. Google developers will keep that very private somewhere on their servers. Okay? So let's get back to our example. We've got a server. The server has a public key and private key. Before we send our sensitive data to the server must send us the public key. What happens next? Well, I'm sure you guessed it. The client will use that public key to encrypt the username, wallet, password, secret data. So now it's just gibberish, completely gibberish. Of course, what this means is that that can be sent now securely over the wire. What happens when it reaches the other end? I'm sure you know the drill. The server receives this gibberish, and it's then going to use its own private key, this blue key, in order to decrypt it. And it's the only one, the only person that can use its private key. Any other private key won't work, because remember, in the previous section, I explained that these two keys, the public and private key, the two keys to an asymmetric key encryption algorithm are mathematically related. This is important. So of course, it can use its private key to decrypt that data into its original form. In other words, it knows that the data now is Wally, the username, and that the password is secret. This is the first concept I want you to understand. That encryption, whether asymmetric or symmetric, protects your data. It makes it confidential. Now I want to pause here. I want you to think about how we can use this technique of asymmetric encryption to allow both parties to exchange a symmetric private key. Because remember, that's our goal. With TLS, you want to eventually end up there where both sets of parties have identical symmetric keys. So buckle up, and I'll see you in the next lecture. Welcome back, and as promised, I just want to discuss very quickly at a high level how symmetric keys can be exchanged between client and server securely. So just remember that that's our goal. We've got a client and a server. Once an HTTP3 connection is established, we know HTTP works with streams, which is bidirectional, and we want both sides to be able to transmit data very quickly and securely. And these are achieved through symmetric encryption and hashing. I'm going to get into hashing later, but in order for this to work, both sides need to have the same set of keys. Now, to make you even more confused, there's not just one set of keys. There are actually 2 pairs of keys, 4 keys in total. 1 pair belongs to the client, another pair belongs to the server. I know, if it wasn't difficult enough, we had to make it more secure, didn't we? And of course, the server has exactly the same set of keys. Now, why are there 2 different pairs? Again, don't worry, I'm going to be talking more about that later, but for now, just realize that TLS conceptually has 2 tunnels. One tunnel is only relating to data being sent from the client to the server, in which case the client's pair of keys, symmetric keys, will be used. And then the other conceptual tunnel, it's not a real tunnel, it's the same connection, but conceptually, we have a second tunnel, which handles all the data sent from the server to the client, and that's used with the server's pair of keys. Now, as to why this is the case, don't worry, I'm going to get into more detail later. But here's the question. How do both sides get these keys securely? And the answer is, well, the server uses asymmetric key encryption. Remember, it's got a private key and a public key. So we can use that concept in order to securely transfer over the wire these symmetric keys. Let's take a break here, and in the next lecture, let's visualize this. Welcome back. Hope you are enjoying and learning a lot. Okay, so I have mentioned this before. We've got different types of encryption, and in real life, HTTPS uses a hybrid approach. It uses both asymmetric encryption, and that's used by the server to encrypt the data using private and public keys, and that's asymmetric encryption. This is what's first established with a TLS connection. But then we want to get to the stage where we've got symmetric keys. Now, there are different algorithms and methods to do this, but I want to discuss a very common one known as RSA. In that case, the client is going to generate a pre-master secret or a code or a string or a value. It's just a random bunch of ones and zeros. The client then encrypts that using the server's public key, sends it over the wire to the server, and then using the same pre-master secret value, both sides can calculate the same set of keys. Now, there is a process, right? The point is, though, that when they create these symmetric keys, they can then use them to encrypt data using some type of other algorithm like AES, for example, going forward, which is a lot quicker. So let me kind of explain, at least at a high level, how this is done. So we know that when a client initiates a connection with the server, the first thing that happens is the server sends the client its own public key. Now, in reality, what happens is the server will actually send that entire certificate. Remember I showed you Google.com certificate? That'll be sent to the client, and inside there, the client can easily extract the server's public key. Okay, so what happens next? Well, this is where it starts getting very interesting. Because what does the client do now with that server's public key? Well, firstly, the browser generates a random pre-master secret. This is independent of that key. And this is known as a seed value. This is going to be used later, I'm going to show you shortly, in generating the symmetric keys. The next thing the client does is it takes the server's public key and it encrypts that seed value, that pre-master secret value. So what does that do? Yes, it obfuscates the actual value itself. It turns it into gibberish. It makes it confidential. So what does this mean, client? Well, it means that the browser can now, of course, send that pre-master secret securely over the wire to the server. When it hits the server, I'm sure you know the drill, right? The server receives this encrypted data. It then uses its private key in order to decrypt that pre-master secret. And the result, of course, is that the server now ends up with exactly the same seed value. You know what? I don't like the name top secret here. As you'll be seeing shortly, we've actually got a master secret. So let me call that top secret. This can just be a secret value, a pre-master secret. I think that's just more intuitive, okay? Now, there's just something I want you to know about this. This entire process that we have just discussed now in relation to how the client generates that pre-master secret, that seed value, and transfers it over to the client, the server, this is known, or using the RSA method, okay, the algorithms. There are others, as I alluded to before, but this is the most common. And, I think it's enough. It serves the purposes of this course in understanding how HTTPS works. I just want to be clear here. This method of exchanging seeding values between client and server is based on the RSA algorithm. This is not the only algorithm. And in fact, a little bit later in this course, I'm going to be showing you TLS 1.3. And TLS 1.3 doesn't use RSA anymore. It uses DHE, the Diffie-Hellman exchange algorithm. So I just wanted you to bear that in mind. It's not the only one. But as long as you understand this concept, they kind of all intermingle with other algos anyway. So it's very important for you to know. Anyway, let's get back into it. You with me so far? I know it can be a bit mind-boggling, but let's move on. I want to now see how these symmetric keys are calculated. Remember, at this point, we've got client and we've got server. Both have this pre-master secret value. What happens next? Well, this is why I didn't want the word top secret before, because now both the client and the server, they'll take that pre-master secret, which is just a random value. They will then combine it with other pieces of data, like a server random and a client random figure. That's another randomly generated value that either party generates during the TLS handshake. So they combine the pre-master secret with that and a few other things to generate a master secret, a top secret value. And why is this important? Well, it's important because it's this master secret. Well, it's that's going to generate a set of symmetric keys. Now, for those of you who are mathematically inclined, how the master secret is calculated is formula driven. In fact, it uses a pseudo-random function in order to do so. It takes the pre-master secret. It then takes the literal string. It's in the RFC itself, master secret. It then takes the client hello random and the server hello random to create a 48-byte value, okay? So what happens now? Well, at this point in time, using this master secret, symmetric keys can be created. Then you can use an algorithm like AES that relies on keys to securely transfer it over the wire. Don't worry about why it's, two sets of keys for the client and two sets of keys for the server. I'm going to be explaining that later. Spoiler alert, it has to do with hashing. Okay. And here's the thing, the server on its side, it does exactly the same thing. So I can just copy these arrows. The server's going to perform the exact same calculation in order to produce the exact same keys. And then to finish off the TLS handshake, the server encrypts all the previous conversations in the handshake using those keys, sends it to the server. The server has to decrypt it. And if it understands it, well, hey, both sides have the same keys. The server does the same thing, and then the handshake finishes, and going forward, they use these symmetric keys. I know this is a lot to take in, and I am moving quite fast. Well, just remember, this was a very long-winded way of me showing you that encryption, whether it's asymmetric or symmetric, is just a way to ensure confidentiality. And that's one of the goals of TLS. What I want to do next, and I mentioned this previously, is that asymmetric encryption using different sets of keys can be used not only for confidentiality, it can also be used to produce signatures. And that provides some sort of basis of authenticity, because we know that only a certain someone can produce a certain signature. So let's take a break and let's see how these signatures work in the next lecture. Adios. Let's move away from the easy encryption mentality. And let's start looking at how we can use asymmetric keys to achieve other things. Now, in order to just explain the concept, I'm going to move away from a client and a server, because in reality, signatures are not produced by the client and the server. It's produced by an independent third party, a certificate authority. So for that reason, I just didn't want to confuse things by having a client and a server. I want to make it more abstract. So what I want to do is I want to introduce a sheriff. And if you know me from my other courses, I'm a Wally Warthog fan. In fact, that's my alias. So I want to assume that a sheriff wants to send a certificate. Think about a certificate authority. Think about google.com certificate. Think about any HTTPS certificate, TLS certificate. That sheriff wants to send a certificate to Wally Warthog. But the sheriff wants to ensure that when Wally Warthog decrypts that message, that Wally Warthog can be 100% convinced that it came from him. How does he do that? Well, this is where we switch things up, because now the sheriff is going to use his private key to encrypt the data. And this is different from before. Remember before, the other party would use the public key to encrypt the data. Well, now we're not doing that. Now, before it even leaves the sheriff station, he's going to encrypt it using his own private key. He will deliver the message to Wally Warthog. Wally Warthog can then use the public key provided by the sheriff to decrypt that data. And by doing so, it's going to prove two things. It's going to prove that the owner of the public key that Wally has, right? Remember, Wally Warthog has a public key. The owner of that public key sent the certificate. And it's going to prove that the certificate was not modified. How does it prove that? Well, if that certificate was modified in any way, and Wally Warthog uses the public key of the sheriff to try and decrypt it, well, it wouldn't work. It would just come up with a random hash, gibberish. So therefore, it would have been modified in some way. Let me draw you a picture. So we've got the sheriff, and we know the sheriff has a public key and a private key. And he wants to send the certificate to Wally Warthog. So like I mentioned, he is going to encrypt that entire certificate using his own private key. Of course, that means that it's going to be gibberish. It's now confidential. He wraps it in a letter, and then this letter leaves the station. It's sent over the wire. It eventually gets to Wally Warthog, and Wally Warthog has now an encrypted message. What does he do? Well, he takes the public key belonging to the sheriff, and bear in mind, I'm making a very important assumption here. I'm assuming that Wally Warthog knows that that public key is the sheriff's public key. That's an important assumption. Anyway, okay, he takes the public key of the sheriff, and he decrypts the message to get to the original certificate. It really is this simple, and this is known as signatures. Specifically, what is the signature here? This here. This here is referred to as the sheriff's signature, because only the sheriff has the private key in order to produce this specific sequence of gibberish. Now, just quickly before I finish, this does not preclude a man-in-the-middle attack. It doesn't stop anyone from the middle intercepting this letter, does it? No, it doesn't. Remember, HTTPS cannot stop this from happening. Okay, all right, I think you've got it. Now we've discussed the fact that asymmetric keys can be used, at least at a high level anyway, for authenticity. But I want to now get on to hashing, because when you include hashing on top of this, you not only guarantee authenticity, but you are guaranteeing integrity. What? Let me explain in the next lecture. See you soon. I want to now introduce you to the concept of hashing. Hashing is very simple. It's not encryption. All hashing does is it takes an input of arbitrary data of any length, okay? And it produces a fixed size of gibberish. This is known as different things, right? It's known as a digest. In terms of TLS and HTTPS, they refer to it as a fingerprint. Don't get intimidated. These are words that just mean the same thing. So when you hash data, you are producing a digest or fingerprint. As with anything, there's not just one algorithm that can be used to hash. You've got different hashing algorithms. You've got MD5, you've got SHA, you've got SHA-2, and a bunch of others. Now let me just show you an example. I'm in Bash at the moment, and Bash has built-in utilities that allow us to hash straight out of the box. I'm on a Windows system, so when I use Windows PowerShell, well, it can't do it. It can, but it's more complicated. You have to jump through a few more hoops. With Bash, it's very, very simple. Now, when you install Bash, it'll come shipped automatically with a whole bunch of inbuilt utilities, and part of those utilities are hashing algorithms. Let me just show you us using SHA. Of course, there are a whole lot of others. Firstly, you can type the word hello, right? And that'll just give us the word back, hello. That's fine. So what I want to do is I want to take the word, let's take the word secret. Why not? Secret. And what I want to do before returning it to the shell here, I want to pipe it. I want to pipe it to another command. Specifically, I want it to be piped to the SHA-256 sum hashing algorithm. And if I hit return, would you look at that? We've just hashed this. We've hashed it out together. How cool is that? What I want to prove to you, though, is that this hashing algo, this fingerprint, this digest, it produces a fixed size hash no matter what the data you give it is. So, for example, we can do another big long sentence. This course is really, 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 really long. Now I can do the same thing. We can pipe it to use this SHA-256 some algo, and we get the same size hash. We can even do the same thing and even perform it on one letter. We get the same size hash. Have you got it? I know, I'm driving the point home. But okay, you know what hashes do? It's one way, by the way. If you have this hash fingerprint here, this digest, it's near impossible to try and figure out that our letter here was A. So you can't reverse engineer a hash. It's a one-way function. There's a few other elements to hash algorithms, like a small change in the input data will produce a very different hash. And then just bear in mind as well, the other thing here, and I did mention this, a hash can take a huge amount or size of data input. I think with this SHA-256 hashing algo can take something silly like, I don't know what it is, 2.3 exabytes in size. So you don't have to worry about these hashing algorithms not coping with a certain message size. Okay, I think that's enough said on hashing itself. I want us to now turn back our attention to the Sheriff and Wally Warthog. I want us to now incorporate hashing. And I want to prove to you that hashing ensures the integrity of data. Come on, come on. Woo! It's getting hot, man. It's getting hot. I hope you're having fun though. And I hope you're learning a ton of information. All right, we've just been discussing hashing. Well, let's get back to our lovely Sheriff and Wally Warthog example. How can hashing be introduced to ensure integrity? Well, and bear with me, it gets more complicated than you may think. Okay, but let's start simple. The sheriff wants to send a certificate. So what he does is that he hashes the entire certificate. All the information in there. Remember, hashing takes any arbitrary size of input and it produces a fixed size hash. So that's fine. We can give this hashing algorithm the entire data in that certificate and we can produce a digest. We can produce a fingerprint. You can literally think of it as a fingerprint because it's literally only the sheriff's certificate that will produce that unique digest. Because if anyone changes even a small item in that certificate, even one letter, remember part of a hashing algorithm is to create a completely different looking hash, even if there's a tiny change in the input data. Okay, so this fingerprint is unique to that sheriff's certificate. It's quite interesting. All right. So what happens next? Well, that fingerprint is appended to the original certificate. Why does it have to be appended to the certificate? Why can't the sheriff, let me ask you this. Why can't the sheriff just send this digest to Wally Warthog? Yeah, why can't he just send that over the wire? That's right, because once the Wally Warthog receives this digest, this fingerprint, remember, it's a one-way function. The Wally Warthog, he will have this fingerprint, this digest, but he won't know how to get back to the original certificate. So that's why the sheriff still has to send the original certificate. But he also sends his fingerprint, his digest, his hash. He wraps this in a letter. It now leaves the station. Now it's in the wild, wild west. The letter's sent over the wire, gets to Wally Warthog. He unpackages the letter and he finds two pieces of information. He finds the certificate and he finds the fingerprint. Now what does Wally Warthog do? Well, he performs his own hash on that certificate. This is why in a cipher suite, both parties have to agree to hashing algorithms. They have to both use the same hashing algo. So Wally Warthog takes a certificate, uses the same algorithm that the sheriff used in order to calculate a digest. And would you look at that? That looks rather familiar. In fact, what Wally Warthog does next is he compares this digest sent by the sheriff to the one that Wally Warthog calculated, and if these two digests are the same, Wally Warthog knows that the information was not tampered with. But I'm sure you can appreciate that there's still a problem here. There's still a security vulnerability. Do you know what it is? Think about what happens when this certificate here leaves the sheriff's station. Don't you think that there's some sort of security vulnerability here? Yeah, I'm sure you would agree with me there is, right? So, let's look at the same example. Sheriff goes through this whole process, creates a digest, it leaves the station. But what happens if a bandit gets hold of that letter and they compromise that certificate? Because remember, Anyone can produce a digest. Anyone can hash a certificate. So now this bandit has produced their own digest, their own fingerprint. But they've poisoned the certificate. It's not authentic anymore. So the blue letter, which is authentic, has now changed to a red letter. The red letter is received by Wally Warthog. Wally Warthog opens it up and it's got a certificate and a digest. Wally Warthog performs his own hash. And would you look at that? This is not good. Because now, this fingerprint here, it does match the same fingerprint that's been compromised. This is a big problem. And don't forget, hashing still performs integrity. It just so happens that Wally Warthog doesn't understand or doesn't know that it's been sent by a bandit and not the underlying sheriff. So what I want to do is I want to pause here. I want you to think about how HTTPS has tried to solve this problem. Spoiler alert, let me give you a clue. We have to combine hashing with asymmetric key encryption in order to solve this problem. So give it a think as to how you think we can use those two aspects to prevent this from happening. I know we are getting into quite heavy concepts here, but trust me, it's very important for you to understand and also realize that all of these individual components you're learning, they are all combined into how TLS and HTTPS work. So there's a very deliberate reason why I'm teaching you about all these things individually. They all kind of come together in the end, you'll see. But anyway, we had the problem before where although hashing ensures integrity, it doesn't really help with authenticity. In the sense that, how does Wally Warthog know that no one's interfered with the data by the time it gets to Wally Warthog? Yes, hashing ensures that whoever sent Wally Warthog the certificate, the actual certificate itself, hasn't been tampered with in that moment. But how does Wally Warthog know that it actually came from the sheriff and not some bandit? Well, that's where signatures come into play. Remember that? We learned that a few lectures back. So let me explain. We've got the sheriff, and the sheriff has his own private key, his own public key, and Wally Warthog's public key. They're buddies. They've known each other for years. So at some point, this sheriff has received Wally Warthog's public key. Okay? We now take that certificate and the sheriff hashes it. He's produced now a fingerprint. You can kind of view a fingerprint being related to the certificate, the actual data itself, because only the original data will produce a exact fingerprint, a digest using a hashing algorithm. If there's any change to that certificate, you know that that digest will be completely different. But that's not enough, as we just saw in the previous lecture. So what do? Well, let's combine asymmetric encryption. So the sheriff takes his own private key and he encrypts the digest. I know, crazy. But now this produces a signature. This is what's known as a signature because only the sheriff has that private key. So therefore, only the sheriff can produce this unique signature. Isn't that cool? Okay, well, let's continue our analogy here. The signature now is appended to the certificate. Remember, you still have to send the certificate because once the data gets to the other end, if Wally Warthog only had the signature, he could only decrypt it into the digest, and that is meaningless. Remember, with hashing, it's only one way. You can't rehash it to get to the original data. So you have to also send the original data itself. Makes sense. Okay. So the sheriff has now appended his signature to his original certificate, and the combined message is encrypted using Wally Warthog's public key, and it's inserted into this letter. It now leaves the station. It gets sent across many miles of land. It eventually reaches Wally Warthog. At this point in time, remember, it is encrypted. It was encrypted using Wally Warthog's public key. So now Wally Warthog is the only one with the private key. He can decrypt it, of course. And he gets two pieces of information in the envelope. He gets the certificate and the unique signature of the sheriff. This is key. This is what's different to our previous example, because now Wally Warthog takes the public key of the sheriff and decrypts the signature back to the digest. And of course, Wally Warthog performs his own hash of the original certificate using the same hashing algorithm that the sheriff used to calculate his own digest. And guess what? They match. I know. That's awesome. So it just proves that the certificate is not changed and that it came from the original person, from the sheriff. And in that sense, it provides authenticity. But think about it. Does it provide authenticity? Kind of, right? Why do I say kind of? Well, let's think about it. I mean, I know if someone does intercept this package over the wire, there's not much they can do, because if they change it in any way, it's not going to help. Why won't it help? Well, because then, these digests will not match. Because remember, Wally Warthog is using the public key of the sheriff to decrypt the signature. Okay, so you could think, Clyde, what's the issue here? Doesn't this solve all problems? Unfortunately, no, because how does Wally Warthog know that sheriff is actually the sheriff and not some sort of bandit? That's an interesting question. And that's exactly why PKIs come into the picture. You need some sort of third party to authenticate. Authenticate what? Authenticate that this key here does belong to the sheriff. And who should provide that authenticity, that confirmation? Well, the PKI, the Certificate Authority, a CA. So that's where CAs kind of fit into the picture, and I'm going to be talking more about that shortly. But before I do, there's something else that you need to understand with hashing. Do you remember I told you that when those symmetric keys are calculated, there's a pair of keys for the client and a pair of keys for the server? Why a pair of keys? Well, one of those keys are used to hash the original certificate. Basically, you take the original certificate and you add a random value to it, and then you calculate a hash of that. I know. Yet another complication. I told you these things get quite heavy, but as long as you understand each individual concept, trust me, it's all going to sink in and make sense soon. So before we get onto the certificate authorities and how they work, let me explain how message authentication codes, MACs, work, because HTTPS uses one of those keys for Mac. Not for Macintosh, for message authentication codes. Okay, I'll see you in the next lecture. Before I get onto certificate authorities, you just need to know about the HMAC key. Basically, we are hashing, but using a private key as well. And this just ensures integrity and authenticity. It's kind of like a double, kill two birds with one stone situation. So remember how I said that when symmetric keys are calculated, there's a pair on the client and a pair on the server. Well, for one-way communication, so here from the sheriff to the Warthog, we're going to be using, and both sides will be using, the same set of shared keys. Remember I was trying to explain that conceptually there's two tunnels with TLS. One tunnel is the one direction that uses one pair of keys, the other tunnel uses another pair. So in our example here, we are only going to use this gold and blue key. Both sides are going to use these same shared keys. But one of these keys are going to be used for hashing and another one for encryption. Let me explain. So the sheriff is here. He knows, that he's been buddies with this Wally Warthog for a long time. They both have, at some point, exchanged these private keys with each other. He's got the certificate. So what he does is he adds onto the certificate his shared secret key. This is just a random value. So he adds a little bit of gibberish to his original certificate, and he now hashes that. Now he's got a very unique MAC fingerprint. What does he do next? Well, I'm sure you guessed it. He appends that to the original certificate, because remember, a digest on its own is meaningless. You can never reverse it. So you always have to send the original data across the wire as well. So now we've combined the message, but it needs to be encrypted. It needs to be kept confidential. Well, guess what? You use that using that shared symmetric key. So now it's encrypted. It's wrapped within an envelope and it's sent over the wire. Now what's very cool is that no one can touch it. It's just gibberish, because no one has those same shared symmetric keys. Of course, it's received by Wally Warthog, who has the same set of keys. He uses the decryption key to unravel the letter and get to the two pieces of information, the certificate and the fingerprint. Wally Warthog then combines his symmetric secret key to the original message and performs his own hash using the same hashing algorithm that the sheriff did to calculate his MAC fingerprint of that message. Of course, he has to now compare the hashes. Do they match? Yes, they do. So it proves that the certificate is not changed since the original person sent it. It gives us integrity. And my dear student, this is exactly how the client and server exchange information with each other over the wire using HTTPS. If you just break it down conceptually like this, it makes sense. Very interesting, because only the sheriff and the Warthog have these same symmetric keys. So we're making an assumption here that Wally Warthog knows and is confident that the only person who has those same set of keys is actually the sheriff. Bringing this back to an actual HTTPS session, at this point, when the client or the server have these symmetric keys, a certificate authority has already been involved that tells Wally Warthog, hey, you are actually talking to a sheriff when calculating these symmetric keys and not this bandit, for example. Okay, so a certificate authority would have already been involved, and that certificate authority uses signatures. You know, like in the previous lecture we discussed here, combining keys and signatures. This is really what the CA does. The other analogy I just talked about now in this lecture, well, that's kind of what the client and server do. So can you see that throughout these lectures in this section, I've been teaching you concepts that are combined in different ways in the HTTPS process. All right, I hope so. But anyway, I want to now focus our attention on, you guessed it, CAs. Why are they needed? What problem do they solve? And once you understand that, you're done. You understand how TLS works. TLS? TLS. All right, so take a break. In the next lecture, let's start talking about the CA authority, how it works. And then I can't wait for the final section where I'll be showing you how to generate self-signed certificates. So hang in there and I'll see you in the next section. Sorry, in the next lecture. Adios. At this moment, I haven't really tackled the elephant in the room. And that is, how do you know that the server you're sending data to is a legitimate server, is a real server? In other words, what if, right, in our hypothetical example here, we're trying to send data to piggybank.com, but what if someone intercepts our message along the way? A hacker, okay, a man in the middle. And what if they pretend to be the real server? In other words, what happens if they switch out piggybank.com's public key with their own public key? Because remember, anyone can generate keys. In other words, how does the browser know that this public key belongs to the correct server? Here it doesn't. It belongs to a hacker. Of course, the browser will then use that public key to decrypt it into random gibberish, send it back over the wire to the hacker. The hacker will then use their private key and extract sensitive data. This is the million-dollar question. We've got this man in the middle. We need to make sure that the server is the one who sends the public key and not a hacker. How do we do that? The answer is PKI. This stands for Public Key Infrastructure. It's a system that establishes trust. How is that trust established? Well, you're going to find out in the next few lectures. Do you remember this slide a few moments back? This is our ultimate goal, where you want the server and the client to directly speak to each other using symmetric encryption. But, as I mentioned, there's an elephant in the room, because how does that client know that it is speaking to the correct server? How does it know that it's received a public key that corresponds to the server it thinks it does? Because let's face it, right? Anyone can generate public and private keys. So that server you think you're talking to could, in reality, be a hacker. How do we solve this? Drum roll. That's right. We solve it via this concept known as certificate authorities. But let's take a step back. HTTPS relies on PKI to authenticate service. What is PKI? It just stands for Public Key Infrastructure, and it's an entire system that involves three parties. So I can even draw it out in a triangle like this, where two of the parties are pretty obvious. You've got the client and the server. But a PKI system needs a third individual trusted party. This is known as a certificate authority. And that certificate authority has to check the public key. It creates a certificate around that public key, and it even signs that certificate. Remember signatures? Remember asymmetric encryption? This is why it's so important to grasp the concepts you've learned thus far in the course, because now it's all going to come together. The CA digitally signs the certificate with the server's public key, so you can be sure that if you're sending a request to a certain IP address, google.com, piggybank.com, that the public key within that certificate, well, it belongs to that intended IP address. Quite interesting. And a client will have to verify that they do trust that CA. That CA can't just be anyone. I'm going to be showing you how that works shortly. But before I get back into HTTPS, I just want to be clear. This entire system around PKI is not specific only to HTTPS. I'm sure you've seen examples of these user account control messages before, all right? My point is PKI is not limited to HTTPS. So let me ask you this. In this example here, when you're trying to download software, who's the client? That's right, it's your operating system. Who's the server? That's right, it's the software provider, aka the publisher in this example. And who's the certificate authority? Well, in this instance, it's going to be the CA that's verifying the code, or software provider known as a code signing authority. Now, in reality, those CAs, the very large ones, they have numerous branches that provide services across different spectrums, not just HTTPS. Anyway, let's take a break here. There's still quite a bit I want to cover. I want to show you how a server requests a certificate. I want to show you then how a client verifies a certificate using the CA's public key. We're going to be combining concepts you've already learned in this course, such as signatures, hashing, and digests. It's going to be interesting. And then thirdly, I actually want to show you another thing. I want to show you that, your browsers have to trust these CAs. In fact, your operating system comes pre-installed with a whole bunch of CAs that it trusts. I know, it's going to blow your mind. Because remember, you need to understand these concepts in order for us to reach our ultimate goal, and that is to spin up our localhost dev server over HTTPS. So buckle up, and I'll see you in the next lectures. This is going to be a super duper quick lecture running you through the process on how a server in the real world gains a certificate from a CA. So the starting point is your server has to generate a public key and a private key. Now, there are numerous ways to do this, and I'm going to be covering that in the next section. But for now, assume you've got a server, piggybank.com. You've now generated a public key and a private key. What you have to do is you have to decide and pick a CA. There are a whole bunch of trusted ones. You can go to anyone, and various CAs have different pricing structures. But anyway, what you have to do is you have to send a request for a signed certificate. This is known as a certificate signing request, or a CSR for short. You kind of have to send information about your organization, and you have to include your public key. At this point in time, the CA has to verify that that public key is owned by the domain name you specify in your certificate, by your IP address. Now, there are numerous ways that a CA can do this. One example is they will request that you add something on your server side, a certain file, certain code. Then the CA can request it. And if it can extract that data, it knows that you are in control of that domain, and therefore it can issue you a certificate. It knows that you control the private key associated with this domain name. Does that kind of make sense? So once it's done that and it's verified, hey, that this person has sent me the correct details, this person is in control of this domain, well, then I'm happy to issue you a certificate. So the CA, it of course has its own private key and public key, but it takes that certificate with all the server's information, organization details, and public key. It then hashes it. We know that that creates a fingerprint or a digest. But this is not enough. Why is it not enough? Well, anyone can just hash a certificate and produce a fingerprint. Remember, we wanting to ensure, by we I mean the client, wants to ensure that this certificate was approved by a trusted CA. Well, in order to do that, we need a signature. So the CA takes their private key, and of course, it encrypts that fingerprint, that digest. And that gets us to a unique signature. Of course, that signature is appended to the certificate. In fact, if we open up a certificate online, I've already shown you that there is a signature in there. But conceptually, you can kind of view them as being separate. And remember that the server's public key is inside that certificate. So now we've got a certificate, and we've got a signature in that certificate signed by the CA. And that's it, my dear student. I mean, it's not that complicated, right? That signed certificate is owned by piggybank.com, and it is public information. But now, I'm sure you're begging the question, okay, I know we've got this CA, but who is this CA authority? Who is this organization? How do I know which ones I trust and which ones I don't? Well, that's a very good question. So let's take a break, and in the next lecture, let me show you that you can view all the CAs on your system. Adios. I want to prove to you that your system, all the browsers that you're using, they have their own list of trusted CAs and intermediary CAs. Just remember that there's kind of a hierarchical system, just like any organization has a CEO, and then under the CEO there are managers, under the managers employees, etc., etc. You can think of it like this. You can't just have a handful of CAs managing every single certificate in the world. They have to delegate, okay? But those delegated CAs are also trusted, and they are on your system. So how can I prove it to you? Well, you can go to any browser, and you can just go into the Settings tab. I'm in Chrome. You can then click on Privacy and Security, scroll down to Advanced, and you can see here Manage Certificates. If I click on that, I can view imported certificates. Boom, shakalaka. So here they all are. There's our trusted certificates in all the organizations. You've got intermediate certificates. You can view the root store just to see all of them in a list. How interesting is that? Okay, that's the one way you can do it. I'm also on a Windows system, and Windows has a graphical user interface called Cert Manager, and that allows us to view and manage all of our certificates on our operating system. So you can actually type Cert Manager, and it comes up here, Manage User Certificates. This is now not in a browser context. In fact, I can close the browser. And here it is. You can view all the certificates that are preloaded on your operating system. We're looking at these trusted root certificate authorities. You can open up the directory called certificates, and here they all are. Now, I'm sure you can appreciate there are actually not that many trusted root CAs. In fact, you can go to Google, you can just type a list of trusted certificate authorities, and it'll just show you a bunch of them. A lot of them you may be familiar with, like DigiCert, Global Sign, etc., etc. But I don't want to lose sight of the purpose of this lecture, and that was just to show you that in order for a site to be trusted by the browser, the CA has to be trusted. It has to be registered on your system and browser as a trusted CA. Now, think about when we create our own localhost environment. We want to be able to host it on an HTTPS connection for various reasons, right? In order to do so, we're going to need a few things. We're going to need a certificate authority to sign our localhost server's certificate. Well, we can easily create a certificate, server side with our own public key. But what about the CA? Which one of these CAs are going to do it for us? Well, the answer is no one. And it is just localhost on our localhost network, which the outside world don't have access to. So we have to then create our own CA, and every root CA has to self-sign their own certificates. I'll show you what that means a little bit later. So we have to do that. Then when it's all done and we sign our server's certificate saying we trust it, we then have to tell our operating system or the browser that our CA that we've just made up, that we trust it. Otherwise, every time you go onto your localhost port, you're going to be getting an error from the browser saying the site is not trusted. Do you want to proceed? You're going to have to click yes. But to get rid of that whole error message, we can just register our CA here. Pretty simple. And I know we have covered a lot. Hope you're learning a ton. Stay motivated and let's keep going. You really have come a long way, so well done. But now I quickly want to run through how a client can trust the CA certificate. What kind of verification is done that makes the client happy that the public key it's received really does belong to the domain name they type in the URL bar? Well, let's just start off here. Remember that every server is going to have 3 pieces of data before a TLS, before an HTTPS connection is even established. Those 3 pieces of data are right in front of you. A signed certificate, they would have generated their own public key and private key. Okay. Now a client comes along, logs into piggybank.com. Now before they even fill in a form, a TLS connection has to be established. So now the browser initiates that TLS connection with the server. And what does the server send the client? That's right. I'm sure you guessed it, but the server is going to send the client its certificate. Now you might be thinking, Clyde, when we examined HTTP3 traffic on Wireshark in the previous section, I didn't see a certificate. Well, the reason is actually it was just cached by the browser. But if we do go onto another site and you capture the traffic on there, you will see a certificate being sent from the server to the client. So that's all good, client. The client gets the certificate. Remember, this is before TLS connection is established. what does the client do with that certificate? Well, it does two things. Firstly, it looks at the certificate and it looks for this signature value. Every certificate includes the CA's signature. And do you remember how the CA calculated that signature? That's right, it just took a hash of everything in the certificate and then it encrypted it using its private key. The client, all it has to do is it looks in this certificate as to who the CA is. Here it's WR2. Is WR2 trusted? Yes, it is. And the client can get the CA's public key by looking at that certificate authority's certificate, all right, easily extract its public key. And that point's actually quite key, right? That's why I just put a separate comment here. Just remember the browser and your operating system, they have all the approved CAs. And they will be using the actual CA's public key to decrypt that signature. So they can't be faked, it can't be given by someone else because your own system has that public key. That's quite an important point. So we've got the signature, the browser then uses the CA's public key to decrypt it, which gets us to the original fingerprint, the digest. Okay, so now we've got a digest. And remember, with a hash, you can never backsolve to get to the certificate. That's why you always have to have the original data itself. This only proves authenticity and integrity that it hasn't been tampered with, okay? So that's the one thing the browser does. The next thing it does is it takes this certificate, excluding the signature of the CA, and it performs its own hash, using the same algos, of course. Now we've got a fingerprint, a hash, and all the browser has to do is compare that hash with the one that we extracted using the CA's public key. And if these two equal, which they do in this case, well then Bob's your uncle. We know, the browser knows, that the CA was the one who signed the certificate, and the server that issued this public key is piggybank.com. Therefore, the only entity that has the private key to decrypt any data we send to that server is piggybank.com. Isn't that awesome? And this does solve problems of a third party impersonating someone else. Just take this example here, for example. And this is going back to the original elephant in the room problem. How do we know we're talking to the correct server? Well, let's assume, a hacker tries to impersonate piggybank.com. So they've produced their own certificate and they send you that certificate. But we're going to have problems here. Why? Well, let's go through the process. The browser receives this forged certificate with a public key. So what's going to happen is the browser is going to look at the certificate and it is going to see a signature. Now this signature, remember, has to be issued by a trusted CA. That can't be forged by a hacker. Why can't it be forged? Well, remember what's going to happen. We are going to, by we I mean the client, is going to decrypt that signature using the CA's public key. So it's going to produce a fingerprint. Now, if the hacker tries to muddle that signature value, well, this fingerprint is going to produce gibberish and it will never match on the next step. Now you might be thinking, Clyde, what if the hacker manages to get the private key of the CA? Well, that's a very good question. And if that happens, well, we're out of luck. That is very, very bad. It has happened in the past before, but it's very rare. And CA security measures are pretty intense for this very reason, okay? Anyway, let's just get back to our example here. We know that this signature is going to produce a unique fingerprint, and that fingerprint hash relates to the original server's certificate. We know that because it's from a trusted CA. Now, what's going to happen if this certificate is forged by a hacker in any way is when the browser performs its own hash and it produces its own fingerprint, we know it's not going to match. We know now that this connection cannot be trusted. Is that kind of making sense? I hope so. I hope so. And yeah, I just want to say well done. You now know quite a lot of concepts. I want to now tie them all together. I want to kind of examine the entire TLS handshake, and you'll be surprised at how far you've come. Stick with me, and I'll see you in the next lecture. Welcome back, and this is going to be a very quick summary on the entire TLS handshake process. Now, before I begin, just realize that QUIC and UDP, they work kind of differently to TCP. With TCP, a three-way handshake has to be performed before we can now start the TLS negotiation process. So HTTP 2 uses TCP. HTTP 3 uses QUIC. QUIC is built on top of UDP. So what I'm going to be discussing here is the TLS handshake process. And this process is kind of the same whether we're dealing with HTTP 2 or HTTP 3. But just realize that before we reach this process, other steps would have had to have been taken by the browser and server. Okay, so I just kind of wanted to get that caveat out of the way. All right, let's begin. It's going to be a heavy lecture, but you'll see just how far you've come. All right, so we know the starting point is that the server has 3 key pieces of information. This is even before a client contacts a server for a TLS connection. The server has a certificate. The server has a private key and a public key. You know this. So let me ask you this. What happens next? That's right. The client is now going to initiate a TLS handshake. And the very first message that the client sends to the server is the client hello. Inside this client hello message, there's going to be a few things that the client sends to the server. Firstly, it's going to advertise a list of cipher suites. You now know what that is. It's the list of algorithms that the client supports in order to establish secure communication. I've already showed you some of the cipher suites used in real life. Next, the client's going to advertise to the server the version of TLS that it supports, version 1.2 or version 1.3. Most likely 1.3. The client is then going to calculate a random number, known as the client random. This is a 32-byte number, a random number, and the first 4 bytes are the timestamp down to the second when the client calculates this value. This therefore makes it very unique to the session. It means that no 2 numbers can be identical, not even the timestamp, if the calculations are done more than 1 second apart. Quite interesting, but that is the client random. Of course, the session ID I've already mentioned. This identifies the actual session between the client and the server. Here's the key thing. I want to keep track of all the information that both sides have. So right now, the server not only has those 3 key pieces of information, it also now has the client random number. The client also has that same number. Okay, you with me so far? It's going to get more complex, I promise. All right, let's move on to the next step. What happens? Once the server receives the client hello, as you guessed it, it responds to some of those things and sends its server hello to the client. So it's going to, by it I mean the server is going to pick one of those cipher suites that the client advertised. It's going to pick the TLS version that the server supports, most likely TLS version 1.3, and it's also going to calculate a server random number. It's going to establish that session ID and something, I forgot to mention above with the client. They are, and they can, also include extensions to the TLS protocol that can be included as part of this client and server hello. But here are the key pieces of information that both sides have now. The client has this client random number, the server random number, and the selected cipher suite used, which specifies what algorithms everyone should be using to establish an HTTPS connection over TLS. You with me so far? All right, what happens next? Can you guess? That's right, I'm sure you got it. The server sends its certificate. When the client receives that certificate, it's going to know the server's public key, and it's going to know the name of the CA that signed the certificate. So let's scroll down. Here we go. The client receives the certificate sent by the server. It now has the server's public key. What happens next? What does the client now do with that certificate? That's right. I feel like you've got this. I feel like you've got this in the bag. The client has to now validate the certificate by using the CA's public key. Now, don't take for granted how much you've learned in this course. If I stated this at the very beginning, you wouldn't have a clue what I'm talking about. Certificate, CA, public key, what? Okay. Well, how does this verification happen? You should know this. The client takes the certificate and it does 2 things. Firstly, it calculates its own hash of the certificate. It hashes it, and that's the result 1. whatever that hash may be. It then goes into the certificate itself, and it finds this certificate signature value. Remember, this is the signature of the CA, and that's done behind the scenes by the CA using its private key to encrypt its own hash of the certificate. So we've got the signature value. Next, your browser is going to take the public key of the CA, and it's going to decrypt that signature, and it's going to get to result 2, which is a hash. And of course, result 1 should match result 2. And if it does, all is good and well. The browser knows that that public key, that it has been received from the server, that the only person who can decrypt any data sent to it is piggybank.com, because they are the owner of the private key that matches this public key. Are you with me? So right now, everything is good and well. We've just been looking at the TLS process. Specifically, the client first sends a client hello to the server. The server then responds with its server hello and its certificate. Now, there is a slight nuance with that certificate. In fact, I'm going to be showing you now that we are able to view the certificate on an HTTP 2 protocol, but not when using HTTP 3. When we are using TLS 1.3, encryption happens a lot sooner. In fact, it happens right after the server hello is given. How's this possible? Well, because a new algorithm is used. Well, not new. It's an algo known as the DHE algorithm. It replaces the RSA algo. What happens is both sides generate a public key in the hellos. They then can use those public keys to generate a pre-master secret that is exactly the same as each other. It's a pretty cool mathematical algo, by the way. So let me show you kind of how that works, all right? So what I've done is I've captured, and we did this before, so I'm not going to go through the whole capture process, but I've captured a request to google.com, and I've just filtered by Google's IP address. That's all I've done now on Wireshark. I've now stopped recording, and we can start examining the client hello and the server hello. Remember, this is all unencrypted thus far. So this initial packet is what the client sends to the server. It's in a quick packet here. And in fact, if we scroll down in Wireshark, we can see here that this client hello is a fragmented message. Luckily, Wireshark, deconstructs it for us quite nicely. We can reassemble it, click on this, and we can actually look at packet number 7 here. This shows us the information we want to know, right? Information related to you guessed it, the client hello. Can you see it? So there's the client hello, and these are all the things we've been talking about. Here's the version number of TLS it supports. Now I know what you're thinking, Clyde, why is it showing 1.2? And I did mention this before, this is more a nuance in the RFC that just has to cater for old school firewalls and software that kind of required certain things to be seen in order not to throw errors. But we are using TLS 1.3, I'll show you that shortly. And then we get to these cipher suites. By the way, I know it's TLS 1.3 because there are only 3 cipher suites. Not much, right? Okay, then we've got all these extensions here. I don't know why they pre-open these up. There must be a way to just collapse everything. Okay, but we've got a whole lot of extensions related to the TLS negotiation process. A few that are important here is this application layer protocol negotiation, aka ALPN. If we open up that, we can see here we are using H3, HTTP 3. We know that already because we can see that it's using Quick, and Quick is used with HTTP 3. Okay, what other extensions are important? Remember, I was explaining, and I am actually in the previous lecture, I'm kind of giving you an overview of how the pre-master secret and the master secrets are calculated based on the RSA key exchange algo, but TLS 1.3, whether you're using HTTP 3 or 2, they've removed the RSA algo and they've replaced it with the DHE algorithm, the Diffie-Hellman algorithm. And I can show you that here. You can look at this key exchange modes. If we open up this, there it is. We can see we are using the DHE algorithm. So we can look at that. If you open up this key share extension and we scroll down here, well, there it is. There's the public key. Oh man, all right, quick cut. You'll notice if you look at the screen in Wireshark, there are actually two key shares going on here. We've got the traditional 32-byte value. This is a public key based on the DHE algorithm, pretty straightforward. However, things are not as simple. In this day and age, when we've got very powerful machines, newer and improved security measures are being introduced. So now we've got a situation where two algos are being advertised by the client to the server, and the one above is much larger in size. It's not 32 bytes, is it? It's 1216 bytes, much larger. And in fact, the server is only going to choose one of these algos. So the first 32-byte value key exchange, well, is rather redundant. So you'll be seeing shortly that when the server responds, it responds with that very large public key. Now the whole process around how that works, it's beyond the scope of this course. But I just wanted you to bear in mind that this hybrid approach is extremely new, and it's just another countermeasure against very advanced cryptographic hacking techniques. Okay, you got it? So I'll show you shortly. I'll do another quick cut to show you and prove to you that the server ignores the first 32-byte public key. All is good and well. So that's pretty much the client hello that we've been looking at. Then we get to the server hello. So if we go down here to packet number 73, we can see here that this is the server hello. You can see supported versions, by the way. We are using TLS 1.3. Proof is always in the pudding, right? I told you we're using 1.3. Okay, we know the server has chosen a cipher suite. So there's a cipher suite chosen. In its server hello, it's also generated its own random number, the server random. Of course, it also has to have created that public key as part of the DHE algorithm, and that's it here, right? Done. I told you. So here's the server response. You can see it's very large. By the way, that truncated square brackets in Wireshark just means that the entire value hasn't been captured by Wireshark. Hope it's making sense. Let's get back into it. So my point is this. Yes, the server will send its certificate to the client after it's sent its server hello in this packet number 73. Okay, but everything after this, from packet 74, which is probably where the certificate is, or actually in packet 75, the problem is everything is now encrypted. No one can see it, unless you've got all the keys, that is. But even then, even if I capture the keys here, you won't be able to see it. Why? Well, it's just a nuance with Wireshark. I think it's just more complicated. They're not quite there yet. They are not as advanced as they are when it comes to handling and decrypting messages with HTTP2. So let me prove that to you. Let me now open up another file. And this file here, I just saved it, by the way. I made a request to wikipedia.org. What I want to do, of course, is I just want to filter not for the Google's exchange. I want to filter for the Wikipedia's one, which is on a different IP address. Well, would you look at that? You can see a whole lot of TCP requests. And you know what I want to do? I see here, you know what, let me just quickly go into preferences. Because I have specified an SSL key log file that all the keys get inserted into, but I don't want to look at that just yet. I want to show you something, right? So let me just delete the reference to the file. This is what anyone can see right now. We get to see all the TCP negotiations, the SYN, syntax. Then we get into our client hello TLS negotiation process. Now everything is the same. Okay, we've got the client random, we've got the session ID, the cipher suites. Look at that, there's 16 of them. Like I mentioned, HTTP2 has a lot more available. When we were looking at the HTTP3 protocol, only 3 cipher suites were available. Okay, and then, you know, everything's the same. The same algorithm, the DHE algorithm is used here. So I don't want to go through that whole process. You can look yourself if you so choose. You can just trust me on that. And then the server hello comes back. Same process. It produces its own random number. It selects the cipher suite used for this HTTP2 session. We are using TLS 1.3, etc., etc. And then because the DHE algorithm is used, everything after this point is encrypted. We cannot read this, right? You can see here, encrypted application data. It's just gibberish. But if we record the session keys in that session log file, well, we'll be able to see stuff. So what I can do, and I did record it when I made this analysis, is we just have to go into preferences again. You know the drill, TLS. And we have to tell Wireshark where all those session keys are kept. And I've just put it into a file called logs.txt. If we hit OK, well, this is great. We start seeing HTTP true traffic. But this is what I want to show you. We see a heading called certificate. And this is the certificate that the server sends to the client. Isn't that cool? And I mean, you can open it up. We can start examining the certificate. Here it is. And you can see all the different things. You can see the length of the certificate, 3,508 bytes. It's got the validity periods, the signature, what algo was used, the subject public key information. This is Wikipedia's public key. Right here. There it is. So we can see it with TLS 1.3. And this is kind of advanced and a nuance with Wireshark. Now, you'll read different things online. I can even go to Wireshark's wiki page and look at this. It says that this private key file, which is our SSL log file. SSL, by the way, is just an old version of TLS. It's deprecated, so we shouldn't really be using it, but for legacy reasons, you'll hear developers refer to SSL. So this SSL keylog file, which, by the way, it's the underlying libraries, the cryptographic libraries. Remember OpenSSL? They're the ones that write into this file. Anyway, we're on Wireshark's site, and they say it does not work with TLS 1.3. But that's just not true, right? Because we have just seen that it works with TLS 1.3. So anyway, just bear that in mind. I wanted to just take some time out here just to show you that these concepts you have learned are very practical and very real. But enough said. Let's finish off with the TLS handshake, because after this server hello, yes, everything is encrypted, but I want you to understand the process of what happens behind the scenes. It's pretty advanced, it's pretty heavy, but I want you to be a grandmaster. It's time to talk about hybrid key exchange. And I did touch on this in the previous lecture, right, when we were in Wireshark. I just wanted to take a time out and expand on this a little bit further, and then we can get back to where I left off in the previous lecture. Okay, so kind of view this as a timeout lecture. What is hybrid key exchange? Well, it all boils down to quantum computers, because they do have the potential to break all those algorithms we are busy discussing right now, like the RSA key exchange algo. But Clyde, what is a quantum computer? Just very high level, it moves away from the traditional classical computers of only dealing with one state at any given time, and that state is represented, of course, by binary, a 1 and a 0. So why the word quantum? Well, quantum computers just use the principles of quantum physics to store and process data. And of course, classical computers, as you know, use binary, 1s and 0s, electrical inputs, on and off. But quantum computers, they move away from that traditional approach and they use qubits. And what really sets qubits apart from traditional binaries is that multiple states can coexist at exactly the same time. Of course, what this means practically for us in this course is that quantum computers, well, they have the potential to solve problems, to crack encryption algorithms that are too complex for classical computers. Have you got it? Okay. That's the gist of it. And there are various organizations that are working on developing algorithms to counteract decryption hacking techniques. One of these organizations is known as NIST. NIST is just a government organization, stands for National Institute of Standards and Technology. A very boring name, isn't it? Anyway, they came up with this algo known as CHEM. Now, there are various algorithms that fall within this category. I'm going to briefly describe to you how this approach works when it comes to TLS, and all of them kind of follow the same steps. So you are going to be learning valuable information. In fact, when we were in the previous lecture, this is the algorithm we were actually looking at. Remember when there were 2 key shares sent from the browser to the server, one of them was based on this algorithm. And it's relatively new. This rollout's only, started by browsers, it's hard to say exactly when, late 2023 or sometime in 2024. In fact, NIST only produced its final set of post-quantum cryptography standards in August 2024. So what you're about to learn is very recent, very real, and enough said. I just want to hop over now to our visual page, and I want to kind of walk through what happens in a CHEM key exchange. Are you ready? Let's hop over to the other screen. You know the drill. I'm just taking a quick time out from the previous lecture. I want to show you how this works. The starting point, luckily, is exactly the same. The client initiates a TLS connection. The first message sent over TLS 1.3 is the client hello. It's inside this client hello where the hybrid key exchange starts. Okay, so we've already seen in the previous lecture this first box. But now, step one is that the client's going to advertise a group of key algorithms to the server. And you can view these algorithms in an extension. Remember, we were in Wireshark, and all I've done is I've taken screenshots to remind you where you can find this information. But in the extension supported groups extension, you can scroll down there and there's this supported groups tab. So here we can see the client's advertising that it can support 4 algorithms. The very first one, I know it says unknown there, but that is this CHEM 768 quantum key algorithm. And I'll be showing you that shortly. Of course, the second one from the top is the traditional elliptic curve algorithm. That's just represented by x25519. I think that's a point, specific point on the curve that's used in the calculation of the key. Okay, so there we go. The client advertises a group of keys to the server. Simple enough. What's next? Okay. The client is then going to send, and we saw this in the lecture, 2 key shares to the server. This is seen in Wireshark in another extension known as the key share extension. I actually opened this up with you in the lecture and I showed you this, but you would have noticed a funny number there, 4588, right? The second key share, by the way, that's the traditional elliptic curve algorithm, x25519. But what is this 4588? Well, they always try and confuse us, but if you go onto IANA's website, this 4588 is this CHEM algorithm. You can check it yourself. There's the website. I've just given you a screenshot here. Okay. And that combines the traditional elliptic curve algo, the ECDH algo, with the CHEM algorithm. So in effect, everything that the server and client need in a hybrid key exchange, well, it's in this very first key share. And that's why I mentioned in the lecture that the second key share, that's actually not used by the server. So you're with me at this point, right? The client's just advertising to the server that it supports a pretty advanced algorithm, and then it's got kind of this fallback key share algo, x25519, the traditional elliptic curve algorithm, the ECDH algo. Okay? You with me so far? All right, Clyde, this is pretty, obvious, pretty intuitive, but what happens now if the server does accept the advanced CHEM algorithm? What happens? Well, that's what I'm going to show you now. Let me just start off by saying, right, that the client does calculate 2 pairs of keys. I just called the one the hybrid key calculation, and the other one is just the normal key, okay? So this normal key, you can view this as the fallback key that the client generates. So it's kind of weird because, yes, processing power has actually happened in order to produce this key, and this is a standalone ECDH key, it's a standalone calculation. But if the server accepts this hybrid key approach, well, we send that public key, this backup key, but it's never used. Sigh. I know, it's just lost, okay? But anyway, when we were in the previous lecture, I actually showed you this key, right? We looked at this key share entry, and here it is. We know, however, that that is actually not going to be used, okay? So you can kind of park that and put that away. The one that we're interested in, of course, is in this hybrid key approach. And at this point in time, when the client sends it to the server is going to have 2 sets of keys. But of course, it only sends the server the public portion of these keys. The client will have on its side its own corresponding private key associated with each of these 2 keys. So remember that with this hybrid approach, 2 pairs of keys are created within this hybrid key approach. Okay, we've first got the client calculating a public and private CHEM key pair and a private and public ECDH key pair. And of course, this can be seen in the first key share entry in the extensions tab. So that key exchange, this here that you're seeing, well, the first portion of it is the ECDH key, and then it's just concatenated with that actual public CHEM key. This is calculated by the client and sent to the server. You with me so far? Okay, great. Well, what happens when the server receives this, Clyde? Good question. So let's look at that. I want to now look at what happens on the server very briefly. It is going to get a little bit complex, but it's super interesting and it's good for you to know this at least at a high level. Okay, so the server at this point in time has received 2 pieces of information from the client in those key share extensions. It's received what I just called it, a hybrid key and a normal key. Now remember, the normal key just contains that x25519, the ECDH key exchange algorithm. And let's assume the server supports this more complex approach, this hybrid key approach. Therefore, that normal key, well, it's just ignored. Okay, you know this already. But let's dig into this hybrid key. We know it contains, from the client, its public KEM key and its public ECDH key. The server then, first off, produces its own set of just normal ECDH, keys, a public key and a private key. It then takes its own private key, which the client doesn't have, and it then uses that with the client's public ECDH key to produce part 1 of a shared secret. Remember, this algorithm is more complex, and that means we're not just dealing with a simple shared secret anymore. It does get more complex, which I'm going to show you now. The second piece of information that the server has is the client's public PEM key. It then takes that key and it performs KEM key encapsulation. Basically just some heavy mathematical formulations on that key, and it produces two things. It produces the second part of the shared secret, and it produces ciphertext. I'm going to be showing you how that ciphertext is used shortly. Because remember, the server doesn't want to send the shared secret over the wire. We want the client to calculate the shared secret by itself, and it must be very unique to only the client and the server. Very, very cool, right? But anyway, at this point in time, what do we have? Well, we've got the two parts of the shared secret, which results in the ultimate shared secret. But it needs to stay a secret. So what the server actually sends back to the client is this key share value. And that key share value is calculated from the ciphertext and the server's public key. Very cool, right? Very cool. So at this point in time, the server's done everything it needs to do. What does it send the client? Well, it only sends the client this key share that it's just calculated. And remember, as part of that big algorithm process, the shared secret has also been calculated by the server. So anyway, the server sends this key share in its server hello to the client. And what's in that key share? That's right, the server's public key and that ciphertext that was calculated, so that the browser can use those two pieces of information. It takes the server's public key, it combines it with its own private ECDH key, and that produces the shared secret, part 1 of the shared secret. Pretty cool. It then takes the ciphertext, it combines it with its own private KEM key to produce the second part of the secret. And of course, at this point in time, the browser can calculate the shared secret, the same shared secret that the server calculated. And at this point in time, my dear students, both sides have the same shared secret, and they can continue with the remainder of the normal TLS 1.3 handshake process. And we are done and dusted. Well, by done and dusted, I just mean that everything is encrypted, right? After the server sends its hello back to the client. And by the way, here's a screenshot of the server hello. This is what we saw in the previous lecture. Here's the server's hello. Can you see it? It's told the client that it's chosen that KEM key exchange algorithm 4588 that combines the ECDH key algos, which we just saw, with the KEM algorithms. So the first part of this key exchange that the server sends to the client, well, there's its public key. It's x25519 public key, and then the ciphertext follows. Isn't this super practical and interesting? I know it is pretty. What happens next? Is the handshake done? No, we haven't reached a TLS session yet. So let's continue the process. Let's continue. Okay, what happens next? Well, now the client needs to verify that the server has the matching private key. Yes, I know in theory, the client has already confirmed it, kind of, by looking at that certificate. But hey, proof is in the pudding, right? And remember what our ultimate goal is. Our ultimate goal is to reach symmetric encryption, where both sides have the same set of keys. And in order to get to that point, we need to use asymmetric encryption. We need to use this server's public key in order to encrypt a pre-master secret. This is how the seed value for the master secret is calculated, which is using the RSA method. Okay, so this is what happens next after the client has received a certificate and verified not only that it was the CA signature, but it verifies the domain name and a few other things. Okay, once that's done, the client is going to calculate a pre-master secret. It's just a random value, and it's going to use the server's public key to encrypt it and send it over the wire. Of course, the server has the corresponding private key, which will be used to decrypt that. So now the server also has the same pre-master secret. It's just a value. So at this point in time, if I zoom out, these are all the pieces of information that both sides have. Are you with me so far? Let's continue. What is the next step? That's right. If you've been paying close attention, you'll know that we have to now take this pre-master secret in order to calculate a master secret value. And that master secret value will be used to generate symmetric keys. And then you can use symmetric encryption, like the AES algorithm, to then going forward exchange data between each other. So that's the next step, right? The next step is we have to calculate a master secret. Now, the way this is done, you just combine different values. Each side has this master secret value. They then combine it with a string of master secret and the client random and the server random. They combine all that information together. They put it through a pseudo-random function to generate a master secret value. We've covered this before, but I hope it's making sense. I hope it's ringing a bell. So now both sides have a master secret. The next step is pretty logical. This master secret is used to generate symmetric session keys. Now, do you recall, my dear student, that when we were examining packets using Wireshark, we couldn't decrypt data unless we had the session keys? And I showed you that one way is to tell the browser to look for an environment variable called SSL keylog, and then we specified a file that all the session keys would get pasted into automatically, okay? Just bear in mind, please, that is quite dangerous. If someone gets hold of those session keys, what it means is that a hacker can analyze all your past conversations with that server and extract data from it. So just bear that in mind. Normally the browsers, they keep those session keys in memory, in their code, and they don't really allow it to be accessible in formats we can read, okay? So it is very secure by the browser itself. But when we start putting it in files like that, just be careful. You don't want that to be compromised. Anyway, these are the session keys I'm talking about. Each side is going to have a set of symmetric keys. The client is going to have a set. One key is going to be used for encryption and the other one's going to be used for hashing. The server also has its own set, one for encryption, one for hashing. By the way those keys are calculated, it's also, it's formula driven. Everything is just formula driven. The master secret is combined with another string called key expansion and the client random, server random, and that's what generates these keys, okay? Now, at this point in time, my dear friend, my dear student, both sides not only have a master secret, but they also have session keys. Why two sets? Do you remember? Well, that's right, the answer's on the screen. But what the client sends to the server will be protected using one set of keys, and what the server sends to the client, that will be protected using the second pair of keys. Why is this done? Can you think of a reason? There are a few reasons. One is, even if the client and the server are sending each other the same data, a hacker will not be able to track conversations because both streams of data, well, they're being encrypted using different keys. So they're going to look entirely different. It's not easy to keep track of conversations. Secondly, if a hacker out of brute force somehow manages to grab one set of keys, well, that's bad, but it's not the worst case scenario because with one set of keys, you can only capture one side of the conversation. It's just another security measure. And this concept of having session keys and using symmetric encryption is so important. So let me just explain what happens with these keys. One last time, okay? When a client sends information to a server, it's going to take that data and it's going to use its HMAC key to randomize that message just slightly with its random key, and then it's going to hash that result. That's known as an HMAC, a hashed MAC. Now, that digest will be sent along with the message to the server. The server then will just take the message now, not the HMAC, it'll take the message, it'll use its shared HMAC key that it has to create a digest, a fingerprint. The server will then compare its HMAC value to that sent by the client, and if they match, the server is confident that the person who sent it has the corresponding symmetric keys. So that's what happens every time a message is sent over HTTPS. Now, do you have to write server-side code to decrypt all these messages, perform HMACs? No, that's what the HTTP protocol does. By the time it gets to your server-side code, all that legwork within HTTPS has been done. How amazing is that? It's quite a useful and cool feature of HTTPS. All right. What happens next? Because right now, we are not done with the TLS handshake. I know, but we're almost done, so stick with me, please. All right, why aren't we done? Well, if you look at our screen, and let me just zoom out slightly here, would you agree with me that both sides of the information have calculated symmetric keys, but how do they know that it's been done correctly on the other side? Well, they don't. That's the purpose now of sending a finished message in a handshake. Okay, so that's going to be the next step. And bear with me, I'm almost done. Firstly, the client's also going to send, and I'm just putting it here because you may see it when you analyze packets. You'll see this change cipher spec record. Now, that's strictly speaking not part of the handshake, but it's just the client confirming that it has everything it needs in order to set up a secure connection. It doesn't need any more information from the server. It's got everything it needs. Okay, but the important thing I want to get across here is that the client is going to send a finished handshake record to the server to prove that it has the correct session keys. Let me explain and show you how this works. So here's the change cipher spec sent from the client to the server and this finish message. This is part of the original TLS handshake and this ends it, okay? It's going to be encrypted, this message here. But what is this message? How is that used? Well, remember that we are going from the client to the server, so we're using the client's pair of session keys. Let's see what happens. So the client, what it's going to do is it's going to take all the handshake messages that have been exchanged previously. The client hello, server hello, the certificate, etc., everything. There's a few others I haven't mentioned. For example, the client or the server will send a server done message as well. There might be a few other things in there. That's all combined and hashed into a digest. But that's not all that's done. The client will then add a bit more data to it, like the master secret, a string called client finished, etc. It's then going to pass it through another pseudo random function, and it's going to generate what's known as verification data. Let's just put this in green with some random text. Okay, that's the verification data that the client wants to send to the server, but now it wants to prove session keys. So what it's going to do is it's going to use its HMAC key to randomize the data, the verification data, and hash it. Then the client's going to use its encryption key to encrypt that hash. Okay, all is good and well, and that's where we get to our wow. That's what's sent to the server. Now, on the server side, it's going to receive that WOW, that random encrypted message. It's going to use its copy of those symmetric keys, right, to first decrypt it to get to that hash, that HMAC value, and then it's going to perform its own set of calculations. Because remember, the server has exactly all the same information that the client does in order to calculate the verification data. It will then use the client's HMAC key to produce a hash. It'll then compare that hash with the one that it decrypted using the client's decryption key. And if they match, the server knows that the client has the correct session keys. How awesome is that? Pat yourself on the back. But Clyde, you're not quite done. And you're right, but we are pretty much done. We have to go through the exact same process, but of course the server has to now do the same thing to the client. So the client knows that the server has the correct session keys, okay? So the client's going to send a finished message, and then the server is going to use its session keys to send encrypted data and that HMAC to the client. The client will then go through the same process, and Bob's your uncle, we're done. Going forward, we are now finished. Both client and server have finished the TLS handshake. They've confirmed that they both have the session keys. And yes, going forward, they use those same session keys and HMAC keys to exchange data with one another. Seriously, I know this was a lot to take in, but you have learned a lot throughout this course. And I don't really want to go into more detail here because, hey, as developers, as front runners on the ground, we want to now apply theory to practice. And that's exactly what I want to do in the next section. I want to show you how you can convert your local host server, whether you're running that server using Node.js or whether you're using another server like live server in Visual Studio Code, for example. I want to show you how we can convert that into an HTTPS session. Of course, you can apply this knowledge to real life, right? To live websites hosted on AWS, for example. That's why this knowledge is so useful for you to have gained. But hey, let me not jump the gun. Smile, stay motivated, and I'll see you in the next section. Now, the moment we've all been waiting for, we're going to be setting up our own server using HTTPS. So let me just quickly run you through the entire process. Firstly, I just want to get terminology correct. Remember, client is the one initiating a TLS collection. And the client, I know in the context of this course, I've been talking about the browser, but it can really be a plethora of things. Emails, Internet of Things, aka smart devices at home, WhatsApp, file transfer clients, your PlayStation, Xbox, and a whole bunch more. And the server, of course, is on the other side. The server is the one receiving the TLS request. And remember, this is the key point. It's the server that needs to be authenticated. There is such a thing as dual authentication, also known as two-way authentication or mutual authentication between the client and the server. And in that case, intuitively, both sides need to authenticate each other before setting up a secure TLS connection. But that's rather rare. Normally, it's the server side that needs to be authenticated. And that's exactly what we are going to be doing. Now, let's just look at this server for a second. Remember, that's the machine receiving the TLS request. In our case, we are going to be creating a loopback server with an IP address typically of 127.0.0.1 because that's reserved for loopback purposes. What do I mean? I just mean that any request sent to this address, typically it's localhost, right? And then we can specify any port we want. Any request sent there will just be returned to the same machine, creating a self-contained environment for testing. And why is this localhost loopback network important? That's right. It allows us to use web servers like Apache, Nginx, PHP, live server, Node, etc., without an internet connection. It allows us to test our sites before going live. In this particular course, yes, the client's your browser, and I want to focus on two web servers. Live server, because developers often use Visual Studio Code, and Node.js. I want to use those two servers in order to spin up an HTTPS localhost. It's going to be super fun. And I have mentioned this briefly before, but just as a caveat, just remember your server needs to understand the TLS protocol. Specifically, it needs to have direct access to its certificate. Remember, we're going to have a CA signing its certificate. That certificate needs to be made available to your server. And of course, in our case, when we're working locally, we're just going to create a dummy certificate. But in the real world, you will have to contact a trusted CA and they will issue you a signed certificate. Is that making sense? I hope so, and I want you to now think about what it is we need from our server side in order to establish a TLS connection. Take everything we've learned. What are the three pieces of information we need? Do you remember? Well, we've got our localhost server. The three pieces of information we need are the private key, the public key, and its signed certificate. Firstly, I just want to talk about this private key very quickly. And I'm going to be showing you the detail shortly. It's fascinating and not many developers know this, but this private key is really the only thing we need to calculate. Because remember earlier on in the course, it was actually in the first section when talking about asymmetric keys that I said that the private key and the public key, they are mathematically related. So therefore, when we create the private key, indirectly, we've already created the public key. So there's not some sort of manual step where we have to calculate the public key. Have you got it? Okay. Let me talk about this private key. How do we calculate it? What file do we put it in? Well, as developers, you always have options. One of the most popular options is putting this private key in a file called .pem. Pem is very widely used to display details surrounding certificates and keys. And don't get bogged down by what a file extension is. All the .pem does is it tells the software receiving your file how to interpret that file. That's all that an extension does. So .pem is telling the receiver, hey, we've got data here related to some sort of certificate or keys. So if we are just including a private key in this file, this is what it's going to look like. You're going to have dashes begin RSA private key, and then it's going to have the base64 encoded data, followed or ended by another set of dashes with the word end prefixed to that RSA private key. Okay, very simple, but it doesn't only have to include private keys like I just said. You can also have the entire server certificate information in a PEM file as well. In that case, of course, you're going to have your RSA private key section, and then you're going to have what's known as this begin certificate and end certificate section. That is the actual certificate without the private key. Do you notice something with all of these? You might be thinking, yes, I do, Clive. What is this base64 encoded data? I'll hand it to you. That's a good question. And that base64 encoded data is actually structured according to another format structure known as ASN.1. So it also, when these files are generated, certain rules are followed as to how that encoded data should be structured. It's only then that it's base64 encoded. Phew, I know. Okay, what do I mean? What kind of encoded data is within these structures? Remember I said the private key includes a whole lot of data that encapsulates, effectively, also the public key. So let's look at how that is formatted. So here's a key format example, structured according to ASN.1. So your key is going to have a whole lot of information, including the version, the modulus. And this modulus, my dear student, that is the public key. The public and private key share that same modulus number. I'm going to be showing you shortly this in action. Of course, the other fields here that are very specific to a private key, which I've listed for you on the screen. Although this is structured in ASN.1, here's the more complicated aspect, is that all of these structures can be formatted according to another standard depending on what information you're trying to structure. For example, if we are formatting a file for a private key, well, it's going to adhere to the PKCS1 formatting standard. So there are quite a few standards working together, but don't worry, it all makes sense shortly. Let's move on. PEM is not the only file extension we can use for our private keys. Another very popular one, and I actually prefer this because it's very clear then what the file represents, and that is the .key extension. .key, the formats and everything, well, it's exactly the same as we previously discussed. It's formatted according to the PEM structure, which in turn is based on the ASN.1, which in turn is based on the packets or PCKS1 standard, okay, because we're dealing with private keys. So of course, a key file is only going to contain our private key, and that, looks stock standard. You've seen this format before. Can you begin to see that with coding, not everything is just black and white? You have a lot of options, a lot of flexibility as to how you want to set up your code and keying and authentication structure. Clyde, enough already on this private key. I've had enough. Okay. So let's get that out the way. We've done with the private key. Let's move on to the public key. But remember, when we create a certificate signing request and receive our signed certificate, that public key is actually going to be inside of that certificate, isn't it? And I even mentioned previously that when we calculate the private key, indirectly we've also created the public key. So for that reason, it's actually in that certificate, and we don't have to separately calculate a public key. Have you got it? Okay, so then what do we have to do next? Well, once we've calculated our private key, we have to generate a certificate signing request. We have to request for a certificate. So let me just briefly discuss this aspect. It's not very difficult, as you're going to be seeing, But this also has to be in a file. Generally, it's in a file called .csr, certificate signing request. And remember, this is for your server, right? Your server is the one generating this file and sending it to the CA. And in order to create this .cs file, we need to have a key pair. We've already calculated a private key, and we already know that once we create a private key, a public key is automatically created as well, because they are mathematically related. They share the same modulus number. All is good and well. So the server has the private key, public key. It can now then generate this CSR certificate, which contains the public key. As you're going to be seeing shortly, this contains information about the organization, its common name, the domains that you want your actual certificate to apply to, etc., etc. All right, Clyde, I see it's quite easy to create a certificate signing request. How does the certificate authority, when it receives the CSR request, how does it know that it actually came from me? That's a very good question. And it's very, very simple. I'll be also in the next lecture just visualizing this with you. But that CSR file, that's actually going to be signed yourself by your server using your own private key. And of course, when your certificate gets to the other side, to the CA, that CA is going to hash your certificate, and it's going to compare that hash effectively to your signature. And if those two values match, hey, it knows that the only person who could request a certificate with that public key is your server, because your server is the only one who has that private key. Don't worry, again, I'm going to be visualizing this in the next lecture. I keep saying developers have a lot of flexibility. And you also have flexibility as to what format you want your file to be in. Remember, I said that this .csr is just a popular convention. But you can also, if you really want, include other extensions, like a .pem extension. Because let's face it, no matter what extension you're using, it's going to contain the same information. And yes, in case you were wondering, we're still following the ASIN.1 format structure of these certificates. But now we're not dealing with a private key, we're dealing with a certificate signing request, and that follows a slightly different format, different headers, different information, for example. So that follows the PKCS10 format. Okay, Clyde, enough of this self-signing certificate request. Okay. So we are done with the certificate signing request. Last but not least, we've got to deal with this signed certificate. How does that work? That's right. In order to get a signed certificate, we need a CA. A CA has to sign a certificate for localhost. Now, no one's going to do that for us, and this is a private network, so I don't want to go through the schlep and hassle of contacting CAs out there, paying money. No. Wally Warthog Incorporated. That's going to be our CA that's going to sign the certificate for our server. Now, what format is this certificate in? It's generally in a format CRT, short for certificate. When we're dealing with the PKI infrastructure, this certificate adheres to another standard format known as the X.509 certificate. Don't get bogged down by all these formats. This is just an international standard that defines the format that we should adhere to. Basically, so every system understands how to read it. Makes sense. And that's all there is to it. I know this was quite a long lecture, but really, take a step back. All we're wanting to do is create three things. A private key. We then have to generate a certificate signing request, after which our server will receive a signed certificate. That's all we are doing. And very briefly, that private key is either in a .pem file or a .key file. And who is this private key given to? It's given to your server. You keep it on your server. You keep it safe. It is private. Next, we've got this certificate signing request. That's generally in a .csr file that's produced by you and given to the CA. It's not private information. Everything on that certificate, well, it's public information. Nothing is secret. Last but not least, we get this signed certificate. That's in the format of a .crt file. And who has to maintain control over that file? That's right, also your web server. And it's public information. You don't have to protect that in any way. So on your server, you're going to be storing a private key file and your signed certificate file. Those are the two most important files that your server needs in order to set up a TLS connection. Of course, behind the scenes, don't forget about Wally Warthog Incorporated, right? That's our CA. That CA also needs its own certificate. And that certificate needs to be given to your web browser or operating system so that it can be trusted. Whew, I know that was a lot to take in. You can even see looking at the screen behind me, we've got 3 types of certificates. We've got the certificate signing request, we've got the actual signed certificate itself given to us by the CA, and then we've also got the CA certificate, which we need to give to our browser or operating system. So this is what we're going to be tackling in the next few lectures together, and I'm going to show you different ways to do this. I want to show you how to use a GUI, graphical user interface, as well as using the command line, using a library like OpenSSL. I'm also going to show you how to do it using Node.js. But bear in mind, all ways of doing this, well, they boil down to what you're seeing behind me. This is all that we have to create. Of course, there are just different ways we can create this chaos of a mess. Hope you're having a ton of fun. Buckle up, and I'll see you in the next lecture. Welcome back. Hope you're learning a lot. Hope you're having fun. I'm going to go very quickly in this lecture because I'm kind of just visualizing what we learned in the previous lecture. Okay. So let's start off with our CA. We're going to create our own certificate authority. Let's just call it Wally Warthog Incorporated. And the first step is that we need to set up the private and public keys for this CA. But as I mentioned, they are both mathematically related, the public and private key. Therefore, we only actually need to calculate a private key. Now, that can be in a file with a .pem or .key extension. I'm just going to call it CA-key. What is the second step? Well, that's right. The second step is that we need to create a self-signed certificate using our own keys. The root CA, the ultimate CA sitting at the top of the chain, always has to have a certificate. But where or who signs its certificate? I know, bit of a circular reference problem. Don't worry, it just signs its own certificate. I know, weird, but that's what happens. And that's not specific to our localhost server. In fact, even if we inspect google.com certificate, you'll see that it's self-signed. Let me quickly show you. So here we go. Here's google.com. I'm going to click on the tab here and I want to view its certificate so we can see it's valid. I can click on that and here we go. We can click on the details section and here's the hierarchy. Sitting at the very top of the hierarchy is this GTS root R1. If I click on that, you can see here that the issuer, well, the issuer is itself. It issued itself a certificate. The GTS root 1? Well, it did. It's self-signed. And of course, this GTS root 1 has to be registered on your browser and your operating system in order for it to be trusted. So I can even prove that too. We can open up the cert manager. Remember that? Here it is. And if we click on trusted root certificate authorities, we'll open up the certificates folder. It should be in here. There it is. GTS root 1. Isn't that cool? Okay. Well, let's get back to the lecture. So our second step is to create a self-signed certificate. And we can call the certificate anything we want. I'm just going to name it CA-cert. Of course, it has to have a .crt file extension. Doesn't have to. I just prefer it that way because it is a certificate according to the X509 standard. And who do we give this certificate to? Where does it go? That's right. It goes to the operating system, or you can even upload it to your browser itself. You with me so far? Okay, so we've done our OS section. We've produced a certificate, a self-signed certificate. We can kind of park that away now and we can get back to our server. What happens with our server? Well, we know that our browser wants to talk to and get data from our localhost. Our localhost server, well, it is a loopback network. It's running on localhost. What is our third step? So our first 2 steps dealt with the CA. Let's get to our server. On our server, the first step is, well, we need to generate our RSA keys, the public key and the private key. In reality, we only have to calculate the private key, and that will give us the public key indirectly. Once we've established our keys for our server, well, then we can move on to the fourth step, the certificate signing request. So there's our certificate signing request. What happens in reality is that will be hashed, and that creates a digest, a unique fingerprint for that entire certificate. How does the CA confirm that it is us with the private key associated with the public key in that certificate? Good question, and I did answer it in the previous lecture. We have to now encrypt that digest using our own private key. So now we've got a signature. Only our server can create this unique signature. At this point in time, that signature is appended to our certificate signing request and it's sent to the CA. Our Wally Warthog Incorporated CA will receive this certificate and it does 2 things. Firstly, It takes the raw certificate itself. It produces a hash of that certificate. Just remember, though, that it does have to hash it using the same algorithm specified in the certificate. For example, it could be a SHA-256 algorithm. And that will produce a digest, a unique fingerprint for that certificate. But remember, we also sent the CA our signature. So the CA then wants to decrypt that signature using the public key specified in that certificate, and that will create a digest. And if these two digests match, the CA knows that the public key in that certificate is owned by the entity that sent the certificate, because that entity is the only one with a private key. For localhost, this is enough. We can stop here, but in the real world, the CA will also want to verify that it is you who owns the domain name. They might ask you to put something on your server, which they will send a request to and retrieve. Basically, you have to prove ownership of that domain name. But we don't have to worry about that because we're dealing with localhost. Okay. So once the CA has gone through this process, what happens next? Is it the fifth step now? Yeah, the fifth step. It's our lucky day. This is the very last step. The CA has to sign our certificate. So of course it sends us back the certificate. And we are done and dusted. We've got our certificate and we have our pair of private and public keys. This is all we need in order to start the TLS negotiation process. But remember, everything is in files. So what I'm going to do, you can call them anything you want, but for the certificate itself, I'm going to put that in a .crt file called server cert. That, of course, contains our public key, which is on the certificate. And where do we give that certificate to? That's right. We give it to our web server itself. In fact, both the private key and the certificate, that has to be kept by our web server. Of course, the second file just relates to this private key. That must be kept private and secure. That can be in a .pem or .key file. I prefer a .key file, but it really doesn't matter. And that's it, my dear student. That's it. Big process. You now know a lot. And in the next few lectures, we're actually going to move away from theory entirely. And I'm going to show you how to start generating all of these public and private keys and the certificates. So I hope you're ready. I'll see you in the next lecture. Welcome. And we are going to get super practical right now. So the first step I want to do is I want to convert our live server, which is just an extension in Visual Studio Code. If you don't know what it is, let me just remove myself. And can you see on the bottom right, we've got that Go Live button right here. And if I hit Go Live, we are now on our index.html page. This is actually executing a live server using Node, by the way, and it fires up a localhost server, effectively. Okay, I know I'm saying I'm running on HTTPS, but that's not the case. Anyways, getting back to live server, I'm just going to kill the server now. If you don't know or don't have it, you just go into the extensions tab here, and you can just search for live server. And there it is, this purple icon, okay? Now that I've got that out the way, let's get to our project here. We've got a simple index.html file, but we need more than this, don't we? What's the first step we need to do? Well, the first step is we need to create our certificate authority. Remember this? Let me just show you here. Wally Warthog Incorporated. We need to set this structure up, which involves two steps. One, we've got to create the private key, and then we have to generate a self-signed certificate. So why don't we do that? Now, there are a few ways we can do it. I want to first show you a GUI. Here's the website. We can kill our local server. And here it is. It's called XCA. That's what the software is called. It's open source. It's well tried and tested. You just hit on this download tab, and depending on what operating system you have, you download it. It's that simple. The next step, of course, is just to have your directory structure set up. I've just created a folder called localhost server XCA. And inside here, why don't we have another folder called XCA related? Okay. Now, once you've installed the software, you can open it up. It is going to ask you to set up a database because all the keys are stored in that database. You know what? Why don't I just show you? So I'm just going to open up XCA. Of course, everything is grayed out right now because we haven't set up a database. To do that, you just go File, New. Of course, we just set up a folder called XCA related, and it's in here that I want to create our database. So I'm just going to call this Certificate Keys Database, just so we know what it is. Now, the software is going to ask you to implement a password if you so want. Because I'm only using this for localhost in a very simple scenario, I don't even want a password on my database. I don't want to remember what it is. So I'm just going to leave that blank. It's now telling us we're insecure. That's fine. I don't care. But now everything is active. We've set up a database. We can now start generating our certificates. Okay. How do we do that? Well, it's very simple. We just click on New Certificate. And by default, because we haven't got any CAs here, we are going to create a self-signed certificate. The default I want to use here is a CA. We're creating a certificate authority, and then we can just apply all. This applies the CA settings across the board. And then you can just literally click on tab by tab. The internal name, by the way, this is the name used by the XCA software. So this is not really used in the PKI system at all. It's just used here for us to, visualize and see which CA we're dealing with. I'll just, refer to our Wally Warthog CA as Wally Warthog CA. The organization name, let's just have Wally Warthog Incorporated. The organizational unit name is just the division within the company that deals with this specific certificate. We don't have to put it here, but just for fun, why don't I just say Certificate Authority Division. This common name is rather important, or more so important than the others. A lot of people just think the common name is the same as organization name. It's not quite the case. In fact, the certificate relates to the common name. So for google.com, for example, you'll see an asterisk.google.com being their common name. So they can have a variety of domain DNS names that apply to the certificate. So just bear that in mind. Of course, we are dealing with the root CA certificate, so it doesn't really matter. In fact, in this case, I'm just going to put Wally Warthog root CA. Very, very simple. Now, if we go back to our diagram, what is the first step? That's right, we've got to create the key. Well, luckily for us, this GUI does it all for us, right? We can click on this Generate New Key tab. We can call the key whatever we want. We're going to use RSA, and you can specify the size of your encryption algorithm. Okay, 2048 bits is plenty enough. You can hit create, and now you've literally created your pair of keys. Well done. Let's move on. Next, we can click on this extensions tab. We are generating a certificate authority itself. You can specify how many years you want the certificate to be valid for. We can be, quite explicit and say 10 years. That's fine. This subject alternative name field is very important. We're going to be using that for our localhost server because you have to specify exactly to the CA what domain names, what IP addresses are applicable to this certificate. So we will be using that later, but not for the root CA. Next, we can click on this key usage tab. I mean, everything's kind of pre-done for us because we selected the CA option at the very beginning. Here, by default, they've highlighted certificate sign, which is what we want to do. We want to sign certificates for our server, and they've also highlighted CRL sign, but we don't really need that. It just stands for certificate revocation list, and it's a list of all these certificates that have been revoked by the CA prior to the expiration. It's not applicable here. Okay, so I've just deselected it, and that's all we need. So we can click OK, and now we've successfully created our Wally Warthog self-signed certificate. Woohoo! Well done. But hey, let's see it. Okay, let's go back to the software, and here it is. At the moment, though, we haven't actually created the certificate. Yes, we have created it using XCA software, but we haven't outputted this into a file. Of course, there are numerous ways to do it, but you can just highlight it, click export, and then it asks you what format. Now, if we go back to this visualization here, you can see in our second step, I wanted to create a file called cacert.crt. So that's all I'm going to do. Of course, don't forget to navigate to your folder that you want this file to be saved into. We put it into a directory called XCA related, and the file name is cacert. And I wanted to have this certificate extension, CRT. Click Save, click OK, and we are done and dusted. In fact, if we go to our directory structure here and we open up our folder, well, there it is. There's our certificate. You already know the format, right, of PEM files. It's got that begin certificate and all this information in between. Well, that, my dear students, contains all the information related to our CA. So pat yourself on the back. Step 1 and step 2 is done. What's next? Let's have a look. Step 1 is done. Step 2 is done. The third step is now we have to generate a certificate and a key pair on our server, on our local host. So the next step is we've got to generate a private key, and we have to then create a certificate signing request. So take a break, and in the next lecture, let's finish this off. Welcome back. Hope you're having a ton of fun. Let's finish this off, right? So let's click on our certificate signing requests. We can make a new request. It asks you for a template. Here I'm going to be creating a certificate signing request for a TLS server. So I'm hitting that option and I'm clicking apply all. We can then go into the subject here. And again, the internal name is just specific to the software. It doesn't get shown to the world and it's not on the official certificate. So the internal name can just be localhost. The common name is important, and I want this certificate to apply to localhost. And hey, our organization name is actually not applicable. I'm just going to put my localhost Sandbox Incorporated, just for fun. Of course, now we have to generate keys. So I'm going to generate our localhost server keys. I'm going to hit create, and it's done. We've got our private key for localhost. Remember that by calculating our private key, indirectly, we've also created our public key. That's why it's not a separate process. Okay, extensions. We're actually dealing with an end entity here, the actual server itself. And this is why the common name is important, because what this software automatically does is it copies your common name and inserts it as a DNS type for the certificate. In other words, we've already set up a DNS field here for localhost. But just for fun, we can also add an IP address. We can add here IP, and we know localhost is on 127.0.0.1. Same thing, if you really want, you can even add a DNS here of localhost. I know it's already been done. I'm just showing you that there is other ways to do it. You can hit apply, and there we go. So this copy CN, it's the same as this localhost. Just kind of wanted you to bear that in mind. And that's all we have to do. I can click OK, and we've successfully now created a certificate signing request. How awesome is that? Okay, Clyde, well, you know, we've done now, if we go back here, we've done the third step, we've done the fourth step. How do we now issue that certificate from our CA? How do we get onto this fifth step? It's so simple. Let's go to the software here. Let's click on certificates. We can now generate a new certificate, but this time it's not going to be a CA certificate. I'm going to use a template here for our TLS server. Now, what's really nice with the software is you can click on sign the certificate signing request, because we've just created one and we named it localhost. So that's cool. And then under this signing tab, we have to specify which CA we want to sign the certificate. So here it's the Wally Warthog CA. That's going to be signing our localhost certificate signing request. Have you got it? I hope so. I hope so. We can click apply all and we can just check the extensions here. Everything seems fine. We're going to issue it for 365 days. That's the validity of the certificate. And then I don't know why it doesn't copy what we just did in our certificate signing request. So we could leave it. Of course, we can just quickly add an IP address here. 127.0.0.1. Apply. And you know what? Why don't we just add a DNS of localhost? I know we don't have to because it is being copied from the common name, but I want to show you maybe you've got a different common name and you'll want to apply the certificate to specific domains, okay? So there we go, done and dusted. And that's all we have to do. We can click OK. We can just ignore the warnings and we're done. If we now click on this Wally Warthog CA tab, we can see all the certificates that it's signed. How awesome is this, my dear student? We are done. We are done. How cool is that? Just quickly, I want to show you something, and this is what causes a lot of confusion. If you double click on this localhost certificate, okay, we can see here that it's been signed by Wally Warthog CA. That's very cool. And our public key relates to localhost. And if we double click on that, this is our public key. Can you see it? 00ABDE. That's what it begins with. This is just in hex format. I'm going to click OK, but just remember 00ABDE. I'm going to hit OK. If we go to our private keys tab, right here, these are the private keys we've generated and that have been saved in the local database we set up. But now look at this. If I click on our localhost private key, oh no, look at this, 00ABDE. In fact, this is exactly the same hex as our public key. And this causes a lot of confusion. In fact, a lot of developers are really confused by this. But don't worry, I'm going to be explaining why this happens. In fact, you already know the answer because I have alluded to it in the previous two lectures, and that is the private key and the public key. They share the same modulus number. And this hex you're seeing here, well, that's the modulus. In other words, this private key is only a portion of the private key. It's not showing us the entire private key. And I'll show you how to see the entire private key soon when we're dealing with OpenSSL. Okay, you with me so far? So now we've got everything we need. But now, what does our server need? Because if we go to our file directory, remember right now we've only got our CA certificate, but we don't have anything else. What are the two files our server needs in order to execute and implement a TLS connection? That's right, the server needs its certificate. And what else does it need? Yes, it needs its private key. Remember, let me go back here. It needs these two files, a server cert file and a server key file. So all we have to do is go into our software, and I want to now export this certificate. It is going to be .crt, and I want to call it server cert. So it's going to be server cert. Pretty simple. And just make sure here, see it defaults to a PEM file. No, I want a CRT file. It's a server certificate file. I'm going to hit OK. And here it is, our server certificate. How awesome is that? We can go back here. We can now click on private key tab. We can click on our localhost, private key, and we can export this. This has to be kept safe in a real world scenario. And I'm going to call it server key. And it's going to be a .key file, not a .pem file. You could do a .pem file, doesn't really matter. I'm going to hit OK, and boom, shakalaka. Here is our private key. Pat yourself on the back. You've got everything you need in order to tell live server that you want your local host to run over a secure HTTPS connection. So take a break here, and in the next lecture, let's finish this off. Adios. Welcome back. And of course, now we have everything we need in order to implement a TLS connection from our server. Now, how do we do it? Very simple. Firstly, I want to create a file in here, called keys. I just want to be disciplined in what we do. And of course, it's empty, but we've got the two required files we need that need to be kept on our server side. Do you remember what those files are? That's right, it's this server certificate and the server key. So I'm just going to highlight them, drag them into our keys directory here. Yep, I want to move them. We can now close that. Okay, how do we tell live server that we want to use HTTPS? Firstly, we are using Visual Studio Code. So what we can do is we can set up a new folder, and you have to call it this .vs code. Now, doing this is so important because in effect, what it does, every time you want to spin up a server, VS Code is going to look whether you have any folder called .vs code, and inside there, it's going to look for a settings.json file. Basically, it's going to ask the question, have you set up any configurations that you want implemented in your project? And of course we do. So that's exactly why I've set up a .vs code directory here. And inside here, as I alluded to, we need a settings.json file. Now you have to call it this. You can't call it any other name. This is what VS Code has been programmed to look for. If you've done any of my other courses, I mean, you'll know that JSON files have to be wrapped within these curly brackets. And every item in a JSON file is effectively, very similar to JavaScript in the sense that it's key value pairs. And what's really nice with Visual Studio Code is it will list a whole lot of them for you automatically out of the box. So you can start typing live server and look at all these settings we have access to. And yes, there is a setting for HTTPS, but I want to just specify, oops, I didn't click tab there. I want to specify the port. That's what I want to do first. Make sure you hit tab. Don't be a muppet like me. And 443 is the default HTTPS port that servers listen on, but I just want to add a 0 because we are in a localhost testing environment. Then in a JSON file, you separate all the key value pairs with a comma. It's that simple. And there are a whole lot here. Live server, you can also set customized browser if you want to use a specific browser. Of course, here we're just using Chrome. But let's get to the heart of the problem, and that is we want to access the live server settings, HTTPS settings. And when I hit tab, look, it does this all for us automatically. It's so, so cool. Of course, it's set to false by default. I want to enable now HTTPS. And in order to do so, I have to point live server to the full URL path of our server certificate and our server private key. Of course, there is no passphrase in our case. I haven't encrypted anything, so we can ignore that. Remember where we put our server certificate? It's in our folder here called keys, and there it is, servercert.clt. Very simple. Just make sure you put the full path to your file here, and we need to deal with / if you're on a Windows platform. So that's all I've done, and I'm going to do exactly the same thing for the key. Done and dusted. Do you think we are finished? There's one slight thing you might have forgot. That's right, we're going to get a warning by the browser saying that our Wally Warthog Incorporated is not a trusted CA. But you know what? Let me show you that warning first before we fix the issue. So I'm on our index.html page. Let me just remove myself. Now you can see I'm going to click on this Go Live button. Are you ready? Okay, let's go. No ways. Come on, pat yourself on the back. We've done it. We're getting a warning now saying, hey, your connection's not private because this certificate authority here, well, you know, the issuer is Wally Warthog root CA, but Chrome has no idea who that is. It's not trusted, and that's why this warning is here. Of course, you can click on Advanced, and then you can proceed to localhost. And would you look at that? I'm now running on HTTPS. Now I know what you're thinking, Clyde, why have they crossed out HTTPS and they've said not secure? Well, just to be clear, we are running on HTTPS, even though that line is there. However, Chrome doesn't trust it. Therefore, they are just warning us. How do we get rid of that warning? That's right, we've got to register that CA, our Wally Warthog root CA, on our system. Now, there are a few ways you can do it. Firstly, I'm just going to close the browser. Let me just kill the ports as well, the server. Like I mentioned, there are a few ways you can do it. One, you can go into your browser, and you would have to do so for each individual browser that you use. Go into the settings, you know, insert the certificate there, or you can just insert it as a trusted CA on your operating system, and that will automatically be uploaded to the browsers, okay? I'm going to do that. So I'm going to use Cert Manager because I'm on a Windows platform. And I'm going to hit Trusted Root Certificate Authorities, click on the tab Certificates, and then all I'm going to do now is I'm going to go Action, All Tasks, Import. Of course, I've got to import the file. Here it is. We're in our localhost server XCA directory. Where did I put it? XCA related, and there it is, CA certificate. If I double click on that, and I hit Next, I hit Next, I hit Next, we'll finish, and we're done. And yep, I'm happy with this. The import was successful. If we scroll down, there it is. Wally Warthog root CA. Done and dusted. So now we shouldn't even get a warning. Let's go to Visual Studio Code. I am going to hit on Go Live. I know I'm in the way, but that's what I've just done. And would you look at that? We don't get a warning. Pat yourself on the back. You really have come a long way. You've learned a lot. But we're not quite finished. There are a few more things I want to cover. See you in the next lecture. Proof is in the pudding. So why don't we use Wireshark and just check that everything is running as expected? Firstly, and I've done this before with you, just bear in mind that I have set up an environment variable here, our SSL keylog file variable, and I've specified that the browser should log all the keys, session keys, in a file called logs.txt. That's all I've done here, been through this before, and here it is. Next, I want to open up Wireshark. I want to now analyze our localhost traffic. And then we can go to our Visual Studio Code here, and I can click on Go Live. Let me just remove myself. There we go. Can you see it? So I'm going on to now Go Live. We know Visual Studio Code will look for that .vs code folder. Inside there's the settings.json file. And would you look at that? We don't get any errors at all, and we are currently running a secure connection over HTTPS. How awesome. All that hard work has paid off, okay? But now, let's go to Wireshark. Let's stop recording. You can see here we've got our TCP connection. Now, the reason why we're seeing more than one TCP since Synack and ACK is because Live Server within Visual Studio Code, well, it's using WebSockets behind the scenes and it's establishing a WebSocket connection. You can ignore that. If we scroll down here, here is our GET request for that index.html page, and we can see it's running on port 54274. So why don't I just filter for TC port 54274. And if I hit return, we only see now the applicable traffic. So here's our Synack and ACK. That's done over TCP. We then enter into our client hello and our server hello over TLS. You have to have a big smile right now. How awesome. And when we look at this server hello, we can even see here that we are being given a certificate. So we can actually open up this TLS packet and we can look at the server hello. We can just keep expanding the appropriate tabs and you can see everything in here. All of the server random number calculated, the session ID, the cipher suite chosen. And we should also be able to see the certificate itself. We can view the certificate. Here it is, certificate. Let me just expand this a bit more. We can see it's 1013 bytes. We can open up that. We can open up the certificate tab. Signed certificate. Who's our issuer? Let's have a look. What? It's this entity called Wally Warthog Root CA. How awesome. We can view the entire certificate here. Here's our subject, meaning localhost, our subject's public key. You can open up that. And do you remember, and I've mentioned this before, the private key and the public key share similar information, specifically the modulus. So I can open up this public key, and what do you know? There's the modulus. It's just very interesting. All the things that you've learned in this course are very practical. Okay, well anyway, that's a certificate that you know our server, our live server, has sent to the browser. Once everything is established, we can actually then issue our HTTP request. Now, you'll notice that we're still using HTTP 1.1. And of course, the protocol being used is HTTP. But please don't think that this is HTTP in the traditional sense. We are running over HTTPS. The only reason I'm able to view this is because I've told Wireshark to look at that logs file for our session keys, because this is encrypted. In other words, although we are seeing HTTP here, it is being run over TLS version 1.3. We can see that directly in Wireshark. So this is a secure connection. It's very cool. You know what I've just noticed? I can't see our server HTTP response. It might be because it's cached. So if we go, you know what, let me start recording again. Yep, I'll start recording again. Obviously now it might be over a different port number. I just want to go to our browser. You have to open up the dev tools here in order to do this, and just long click on the refresh button and then go empty cache and hard reload. If I do that, now we should see the server response. If I scroll down, here it is. Here's our server response. I can actually stop recording now, can't I? And we can, now filter on a different port, 54281. So we can filter for TC port 54281. And here we go. There's our GET request, and here's the server response again being run over HTTPS. And if I expand this here, we can actually view this packet data here, the actual payload itself. We can open that up, and there it is. Here's our actual HTML that has been decrypted. We can read it. Anyway, this is enough. You know a lot of this already. I just kind of wanted to prove to you that our entire setup, it's done. You've literally done it. But hey, this was only part one, right, of what I want you to learn, because next I want you to learn how to use a command line interface using a library like OpenSSL to establish a secure connection. In effect, I want to do exactly the same thing, but moving away from a graphical user interface. So I hope you're ready. Buckle up, and I'll see you in the next lecture. We are going to be using a library known as OpenSSL in order to now generate all the certificates and keys we need to spin up our server on a secure TLS connection. So obviously you need OpenSSL. Now, if you're on Mac or Linux, I believe that's pre-installed on your operating system. You don't have to do anything. If you're on Windows, it may be installed if you've used certain packages and those install OpenSSL to check whether you have it. All you have to do is open up a terminal window. I'm using Bash here, but you could also use PowerShell, and you can just type OpenSSL. Now, if you hit return, you should see all the commands we can use with OpenSSL. Very cool, right? So in order to, generate our keys, we're going to be using genRSA. We're also going to be using the RSA command. And you can see here that they have a whole lot of digest commands, hashing algorithms. You've already seen SHA-256. Here's MD5. Those are very popular. We've got a lot of ciphers that we can use in terms of our TLS negotiation process. It's very cool. Okay, but if you don't have it, what do you do? Well, again, I'm assuming you're going to be on a Windows system. The easiest way is to just go to this website here and download it. They've got a very easy way to install it. You can just pick which version you want, probably the first one, and you can install it on your system. It really is that easy. And once you have it installed, once you can type OpenSSL in the command line, well, then you're ready. So make sure that's all set up properly, and let's get cracking in the next lecture. Welcome back, my dear student. So now you've got OpenSSL installed on your system. Well, let's get cracking. Let's start generating everything we need. All I've done is I've copied the exact same, folder structure we had before, but I've renamed it now to localhost server _ OpenSSL. Everything should be the same. We've still got a folder called VS Code. In here, we've got a settings.json file, but now I've got to change the directory here, don't I? Because our certificate is not going to be in the old directory. It's not going to be in the XCA directory. It's going to be in the OpenSSL directory. And of course, that applies to both the certificate and the key. Now with Visual Studio Code, it's really nice. I can press Alt, and then I can click on this other XCA word, and now I can affect or edit text in two places at the same time. So I'm just going to remove XCA and I'm going to replace it with OpenSSL. How easy was that? And of course, I'm going to name our certificates exactly the same thing so everything else can stay the same. Okay, I'm going to save, close that file. Done and dusted. Of course, our key folder here is empty. I deleted those keys. We're going to be generating them via OpenSSL. Next, I know a lot of these commands can get quite heavy. So I've produced a file here. We have outlined all 5 of those steps for you with all the bash commands. So I will include that as part of the lecture. But hey, without further ado, let's get cracking. What I'm going to do is I'm going to click on this OpenSSL related folder. I'm going to right click and I'm going to open this in my integrated terminal within Visual Studio Code. OpenSSL, and all the commands are now shown. Very, very cool. Okay, let me clear this. And what's the first thing I want to do? I've got it in my MD file here. By the way, an MD file is just a common extension used for writing README files, instruction files. You'll see what I mean when you start looking at the file. But anyway, step 1, we know is we need to deal with our CA. We need to generate a private key for our certificate authority. So how do we do that? And I'll walk you through each of the commands just so it really is intuitive and you understand exactly what it is we're doing. Okay, so in order to use OpenSSL, you have to type the word OpenSSL. I then want to generate our keys. So we use the command gen_rsa because we're using the RSA algorithm to produce those keys. And that's pretty much all we have to do. However, I want a file. And in order to do that, I use the -out command in OpenSSL. I want to output a file somewhere. Now, we didn't explicitly generate this file when using XCA. We didn't have to, but here we do. So I want to output this file in the same directory. So that's what will automatically apply here by using the out command. I don't have to rewrite the directory we're currently in. And I want to call it CA key. Now, of course, you can put it in a .key file, or, and I'm just going to do this to show you something different, we can use a .pem file. Now, the other thing is we could encrypt this private key file. Remember the passphrase. Actually, I can show you here in our VS Code settings.json file. This passphrase here currently is not encrypted, right? Our key file, which is why I didn't give it a value. However, if you do want to encrypt your private key file, you can just supply an encryption algorithm. For example, using AES 256. If you want to, you can do that and you'll be prompted for a passphrase. I don't want to do that. I'm just using this for localhost. And although many developers will say, hey, even for localhost, you should always encrypt and protect your private key. Well, I just disagree. I don't think it's important. There's nothing I'm exposing here. So I don't need a passphrase for this example. Okay, I'm going to hit return and we should be done. You can even see here, here's our file, our CA key. This is in PEM format, so we know it has this structure. You've seen this before. Let me just zoom out. And there's our private key for our CA. Why is this needed? Well, it's just needed by OpenSSL when we now approach our second step, and that is creating a self-signed certificate. Remember this, our Wally Warthog Incorporated CA, well, the first step is done. We've created our CA key.key file, .pem file. Now I just want to move on to the second step, and that is to create a self-signed certificate, which we put into a certificate called cacert.crt. So let's do that now. Let's close this CA key.pem file. Let's expand our terminal, zoom in slightly. By the way, you might be thinking, Clyde, when I used XCA, sorry, I know I'm backtracking a bit, but it's important here. This passphrase is blank. If you are using XCA and you want to have a passphrase, it's actually very easy. All you have to do is open up your certificate keys database file, right? I did this previously with XCA. Go to the private keys section, click on your localhost private key, right click, and you can change password. Okay, there. It's that simple. It's that simple. Just wanted to kind of let you know that you can do it using XCA. How do we now move on to step 2, and that is creating the self-signed certificate? It's very easy. Again, we use the OpenSSL command to tell the terminal that we are using the OpenSSL library. Here I'm going to use the request subcommand, req, and this is used to request new certificates. This can either be a self-signed certificate or a certificate signing request. We're going to have to use that for our server. In this instance, I want to create a new self-signed certificate in the X509 International Standard format. I just want to tell, OpenSSL that I'm not generating a certificate signing request. I actually want the end certificate itself. Of course, that certificate contains numerous things, doesn't it? Including the hashing algorithm. So here, let's just say we want the SHA-256 hashing algorithm. Next, we can specify the validity period of our certificate by using the days option. And we can just say this is valid for 365 days. And now remember I said that that private key is used, that one that we just created, that ca-key.pem file. Well, this is why we need it, right? This command needs that private key in order to generate its own self-signed certificate. So we have to use the key option, and then we have to tell OpenSSL on which file the key is in. It's in the file called ca-key.pem. And then I want the output of our certificate to be placed in a file in this directory. What do we want to call that file? That's right, we want to call it cacert.crt. And that should be it. I'm going to hit return. And this is a problem now. I'm assuming this is happening because we're using PowerShell and not Bash. So let me open up Bash. I then want to navigate to a certain directory. So I'm going to change directory with the cd command. And I'm going to navigate into the one called OpenSSL related. I hit return. We should be good. Yep. And now, if I just use exactly the same command and hit return, hopefully it works. Oh man, this is beautiful. Okay. Remember, I told you that certificates have other information. And when we were on the XCA platform, we had to fill in certain details, like the common name, organization name, etc., etc. So we can do that here. We actually get prompted by the terminal. Country name, I don't care. State or province, don't care. Locality, I don't care. Organization name, doesn't really matter. But to keep it consistent, we'll just put Wally Warthog Incorporated. The organizational unit name, again, just to keep it consistent with our previous example, I'll just say that this is in the certificate authority division. Last but not least, we've got the common name, and that's, generally has to relate to the domains, but here we're dealing with a root CA. So you generally just put the name of the CA here. Wally Warthog root CA. Email address not applicable, and we are done. Here is our CA certificate. I can't believe it. Done and dusted. So getting back to our pretty diagram here, step 1 and 2 is done using OpenSSL. Now, before I move on to step 3, 4, and 5, which is very easy by the way, I want to just dig deeper into the problem we had when we started examining the private key and the public key. They kind of looked the same, didn't they? So I want to tackle this head on. I want you to see firsthand how to extract the public key from the private key. Because if we go to our directory here, well, we can look at our private key, but we know within there, we can extract the public key. So I'm going to show you how to do that. And I'm going to show you why at first glance, it seems like the private key and the public key look the same, but they don't in reality. So take a break. And in the next lecture, we're going to tackle this problem together. Adios. Welcome back. This is exactly where we left off. And let me just state the problem of, the keys looking the same, the private key and the public key head on. So let's go to our folder directory here. Now I want to use XCA to open these up because I want to show you something. Okay, firstly, let's open up our private key using XCA. I want to now open up our public CA certificate. So there we go. Here they are, side by side. We know we're dealing with Wally Warthog root CA, and we can show this public key. But what is going on? Can you see that the public key and the private key, well, they match? Isn't this a problem? Aren't people now viewing my private key? Well, no. And I want to prove it to you. Okay, so firstly, what I want to show you is I want to show you how to extract the public key from the private key. In order to do this, let's go back to Visual Studio Code and let's just navigate to our bash terminal. Again, I want to use OpenSSL, so I have to type in the keyword OpenSSL. Now I want to use the RSA subcommand because I want to start manipulating and working with our RSA keys. Now in this case, I want to give the algorithm an input file specified by the -n command. The name of the input file I want to give is our private key, which we put into a file called cakey.pem. And I want to tell OpenSSL to publish our public key. In other words, to output the public key, pub out, from that input private key file. Is that making sense? Of course, I want it outputted to a file so we can examine it. And in order to do that, we use the out option. And I now have to specify the name of the file, which I can call CA public key. You can have it in a .key file or a .pem file. It doesn't really matter. I'll just put it in a .pem file here. And if I hit return, you should see it inserted into our directory. Would you look at that? So this is the first thing I want to show you. If we look at this public key.pem file, let's just close the terminal for a second. And side by side, I want to now look at this CA private key. Well, would you look at that? They are different, aren't they? Look at that. Look at how much more information is in the private key than the public key. So already at first glance, we kind of know, hey, these are not the same. Okay, Clyde, I get it. They're not the same, but I want more proof. What is part of their private key? How do I extract the details of their private key in readable formats in a way that I can read and see? Good question. There are a few ways to do it. Just remember that this entire public key, yes, it's in PEM format, but remember in earlier lectures, I explained that within PEM, depending on the information displayed, various other structures and formats are followed. In this instance, we're following the ASIN.1 format. And hey, there are a few ways we can deal with it. Firstly, let me show you a way in the terminal itself. And let me just zoom in here. It's very simple. Again, we're using OpenSSL. We're using the RSA algos here within OpenSSL to now read that private key. So I want to give this algorithm the input file, which we do by using the -n command. We called the private key cakey.pem. Now I don't want to output it to another file. In fact, I only want it to display the context of that private key here in the terminal itself. To do that, I can use the text option. And I want to be explicit by saying I don't want an output file. If I hit return, I hope you are smiling, okay? This is all the information contained within your private key. How interesting. It's got the prime numbers, it's got the modulus, the private exponent, but this public exponent, okay, that's also used by the public key, and this modulus. Well, that's common between the private key and the public key. And can you see this hex? Does it look familiar? It starts with 00A892. And if we go to our XCA here, which we were just on before, well, would you look at that? It's exactly the same hex number. 00A892, etc., etc. So proof is in the pudding. These hex values are representing the modulus of both the public key and the private key. Is that making sense? Now remember, I did promise you that there are more than one way you can do this. We used OpenSSL, but you can also use a graphical user interface. In fact, if you navigate to this website here, which ironically is not secure, even though we are on a course all about security, okay, but it is fine. What we can do here is this is an ASIN.1 decoder. And we can be very specific. We can say, well, we want to go from the PEM file to ASIN.1 format. And then we can just paste in our file here. So we can go to Visual Studio Code. Let's just close this terminal. We can close it entirely. We don't need a split view anymore, do we? And I want to go to our private key and I want to just paste everything. You can literally paste the whole file. Control A, select everything, and Control C, copy. We can now go to the website here, input that, and then we can click on this button called Convert, and Bob's your uncle. This is what the ASIN.1 format looks like. Don't worry about all these words like UP sequence and UP integers. These are just tags used by the ASIN.1 formatting structure to specify different types of data. The structure is used just so different programs all over the world and different organizations know how to pass this information. Okay? You know, for example, this UP sequence just specifies that the data structure contained here is just a sequence of elements. The next UP integer value here is the version of the key structure used. Here, version 0. This nested sequence here just gives a few other pieces of information relating to the algorithm used here. And really, you know, I don't want to keep boring you by going through each line item. You know, this first octet string, this is just the binary format of the key. What's interesting to us is this one here. This first integer value is the modulus. And you'll notice it's the modulus because it's the same hex value, 00, A8, 92, etc., finishing with double D. This is the modulus. Of course, the remaining items are all the other prime numbers and exponents related to the private key. Have you got it? Is it kind of making sense? It is quite advanced and many developers get hung up on this. You now know a lot more than others do. And yes, we don't actually need the public key extracted. It is on the certificate itself, so I can just delete this file. Okay? Well done for sticking with me, if you have stuck with me this far. And now let's get back to the problem at hand. Okay, we've done with step 1 and step 2. We've created our CA. I want to now turn our attention to steps 3, 4, and 5. I want to now look at our server. I want to generate these keys, the private key, and then I want to generate a certificate signing request. So let's pause here and let's pick up in the next lecture. Adios. Welcome back, and by now you know the drill. It's not that difficult, is it? We have now created our CA. The next step, of course, is to deal with our server side, and our server needs 2 files, a server key file and the actual certificate. But of course, we need our key pair before we can get that server certificate. So that's what we're going to do now. We're going to create our server key. It's very simple. Of course, now we've only got 2 files, don't we, related to our CA. So what I want to do now is open our terminal. I want to just navigate to the correct directory by using the cd command. The // is just telling bash I want to navigate in the same directory, but now in a folder called, what's it called? OpenSSL related. It's that simple. All right, so now we are in the correct directory. And how do we create a private key? We did it for our CA, do you remember? That's right, we've got to use the OpenSSL keyword. And then I want to access the generate RSA key command, and I want to output it into a file called what? That's right, called server key.pem or .key. It doesn't matter, you could use both. I'm just going to use .key. And now, if you want to, you can specify how many bits you want your key to be. For example, 4096 will make your key very, very strong, okay? I don't want to do that. I just want to stick with the defaults. So I'm going to hit return, and here is our server key. How easy and intuitive was that? Final step, of course, is to produce a certificate signing request, a CSR. There are a few ways you can do it. Remember that we have to specify those subject alternative names, the domain names we want our certificate to apply to. How can we do that? Okay, well, first I'll show you the manual approach, and this involves creating a configuration file. So in our OpenSSL related directory here, I can create a new file called config.cnf. I'll just collapse the terminal window here, zoom in slightly, and collapse this panel. In the context of TLS certificates, a CNF file is just used with OpenSSL to configure certificates, to provide options to certificates. That's what we want to do here. And it does require a strict formatting style. And I'm not going to go into the syntax here. I'm just going to paste what I have on my other screen because I've done it previously. But this is where you can specify your hashing algorithms. I don't want prompts by the command line when I create my certificate signing request. That's why I've said no here. The distinguished name I've specified is in this field, this request distinguished name property. And in here, I want our common name to be specified to be localhost. And this is where I want our subject alternative names to be. I'm pointing it to our alt names property here. And I want our DNS to be localhost and our IP address to be 127.0.0.1. You know this, and this is kind of just how it has to be formatted in this specific file in a way that OpenSSL can understand. So this is the one way we can do it. Of course, we can go back now to our terminal and we can produce our certificate signing request. How do we do it? Well, you know the drill. We have to access the OpenSSL command by using the keyword OpenSSL. I want to now use the sub command request because we are now requesting to produce a new certificate. By the way, that's why I'm having -new option here. But this time I don't want an X509 certificate, do I? No, I want a certificate signing request. So I'm not going to put the X509 keyword. This will automatically create a certificate signing request. And I need to specify the private key of the server and the configuration file that we've just set up in order to create the certificate. So firstly, let's deal with the key. Where's that? Well, if we look at our folder directory here, we know it's in a file called serverkey.key. I want to now output our certificate signing request. And in order to do that, I'm going to use the alt option. And we can call the file anything we want. I'm just going to call it server CSR in a .csr file. And when OpenSSL generates this file, I want to specify or give it config options. All I have to do is point OpenSSL to our configuration file, which we put into a file called config.cnf. And if I hit return, Bob's your uncle. We're done. Here's our server CSR file. How intuitive was that? Begin certificate, end certificate. Man, this is so intuitive once you understand the process. Of course, there are many ways you can achieve it in programming, okay? Let me just clear the console. So that's the one way we can do it, by creating this manual config file. But hey, you don't have to have this separate config file. So let me grab this config file and let me delete it. I know, bold. Okay, we can even delete this CSR file because I want to show you another way to produce it. What we can do, we can access OpenSSL. We want to request a new certificate, but this time also a CSR, so I'm not telling it to produce a X509 certificate. I've got to, of course, point it to the server's private key, which is in a file called server-key.key. I then also want to produce a file in this directory, and I want to call the file server.csr.csr. Now, we can supply those extensions directly in the terminal. We just need the prefix or the option subject, subj, and now we can specify extensions, options that we want to give OpenSSL. The first one is the common name. Now, if you're on Mac or Linux, you can use \cn equals and then the name of your, server. In our case, it's going to be localhost. That's going to be our common name. But I'm on Windows, and Windows has a bit of a problem with that syntax. In order to fix that problem, you just have to use 2//cn and then localhost. Just bear that in mind. Windows. I then want to add extensions, so I can use the add ext option to this. And what extensions do I want to add here? Well, it's going to be the subject alternative names, our server's domain names. I can do that here in OpenSSL by, specifying the exact extension I want to populate. And I have to use their words, right? Subject, alt, name. And here I want to access our DNS record, and that can be set to localhost. But that's not all I want. So I'm going to put a comma, and I also want to specify the IP address. The IP address is what? That's right, 127.0.0.1. Don't forget to finish off with the closing quotation marks, hit return, and we should be done. No way. Cool. So there's our server, CSR, begin certificate request, end certificate request. Done. And we used purely the command line in order to achieve that. So well done. Welcome back. And you know the drill. Right now we've got our CA cert, CA key files. That's all related to our certificate authority. We've generated our server key, and we've generated a server certificate signing request. The final step, of course, is to sign that request by our CA And then we are done. We have everything we need in order to spin up a TLS server. Remember, this is our diagram, and we are on this final step now. That's what we have to do. And it is so simple. All we have to do is use the OpenSSL keyword. You know the drill. I now want to generate an X509 certificate. And I can do so using the request option. I have to specify the input files that the CA needs in order to generate this certificate. And what is that input file? That's right. It's the server CSR file. I then need to provide OpenSSL with the CA certificate, which we put into a file called CA cert. And I also need to give OpenSSL the CA's private key, which we put into a file called cakey.pem. It could also be in a .key file. It really doesn't matter. I then want to output this into a file called what? Server cert. That's what we called it, didn't we? We can specify the validity period here being 365 days. We can specify a hashing algorithm to be SHA-256. And now, do you remember we specified those extensions in the previous lecture? Those subject alternative names, the DNS of localhost and the IP address of 127.0.0.1. Well, I want to copy those extensions when generating and signing the certificate. In order to do so, we can just use the option copy extensions and then tell OpenSSL to copy those. Okay, I can hit return and we should be done. Wait for it. Would you look at that? Here is our server certificate. We can close the terminal because now, my dear student, we are done and dusted. In fact, I can navigate to the directory of this file and I can open up this server certificate in XCA. Just have a nice representational view of what we've just created. We know the issuer is Wally Warthog Incorporated. The subject is us, localhost, and here are our extensions. And my dear student, this is what we just copied. Our DNS of localhost and IP address. Very, very cool. So now everything should work as expected. We have everything we need to set up an HTTPS server using live server. But before I show you how to do it, I want to pause. I want you to try do it on your own. And in the next lecture, it'll only take a few minutes and let's spin everything up. Adios, and I'll see you soon. Did you give it a go? I hope so, and I hope you're having a ton of fun. Whew, you've learned a lot, and you can apply this knowledge, of course, to real live websites. So don't take it for granted what it is you've learned. Anyway, we've got all the files we need. In fact, we only need 2 files, don't we, on our server in order for live server to work. What are those 2 files? That's right, it's the server certificate and our server key. And if I drag those into our keys directory here, yes, I want to move them. Well, we can just ignore now the OpenSSL related folder structure. We don't need it anymore. These are the 2 files we need. And everything else is set up. We've got our VS Code folder here, and in here our settings.json file. Because we called our files exactly the same, we don't have to do anything else. Everything is set up. So we can just go to our index.html file, hit go live, and we can wait for it. Well, would you look at that? We can go advanced, we can proceed, and we are now running over HTTPS. Of course, to remove these warnings, all you have to do is go into your OpenSSL related folder here. You know that you have to grab this CA certificate, and we have to copy that onto your operating system or into your browser. Once that's done, you won't get a warning anymore, and everything will operate as it did previously when we used XCA. But well done, we're now running over an HTTPS server, and we did it via the command line using OpenSSL. Pat yourself on the back, well done, but we are not quite done, are we? Because task 3 is to do this using Node.js. Right up until now, we've only been using live server. I want to show you now how to configure a Node server to do the same thing. I can't wait, and I'll see you in the next lecture. Welcome back. Thank you for sticking with me, and well done for sticking with me thus far. We are almost finished the course, which is always a bittersweet for me. But hey, I'm constantly producing more, and I hope to see you in another course soon. But anyway, let's get to our Node project. I want to use a Node package called makecert. Now, there are 2 ways we can use it. We can use the API approach. Basically, we can write code to generate the certificates. That's what I'm going to do first. I've actually set up a directory here called localhost server node API. Next, I'm also going to show you how to use makecert in the CLI, in the command line interface, to produce the certificates, and then we can just use them in our project. Okay, so let's get cracking. Of course, we have a blank directory. I want to create an app.js file. This is going to be our starting Node entry point. In effect, this is our server-side code. This is where we write Node. And as you know, we write Node server code using JavaScript. That's right. Okay. The first thing I want to do is I want to import all the required modules. And I'm going to be using ES module syntax. It's very intuitive. You use the import keyword. Then you have to name the module. Here I want HTTPS because we're going to be spinning up an HTTPS server. And then you use the from keyword. And it's from a module called HTTPS. Luckily for us, this is native to Node, so we don't even have to install it. Of course, you can kind of see it's slightly grayed out here. Don't worry. That's just because, of course, we haven't used it yet in our code. Next, I want to import a file system object from the FS module. Again, this is native to Node, so we don't have to install it. Well then, Clyde, what do we have to install? Well, okay, let me import Express. Express is just a framework that simplifies code. Now, I don't have to use it here, but you'll see many developers that use Node use Express. So for that reason, I'm just going to show you how to use it. In effect, it's only going to be used really to serve a server response to a GET request to localhost. You'll see what I mean soon. The module, of course, is called Express. That we will have to install. And the one other thing I want to install now is the makecert package. I want to actually import two objects from this package. One is called createCA. Another one is called createCert. CreateCert, by the way, well, that's generating all the server-side certificates and keys. And the createCA intuitively creates our certificate authority. The module is called makecert, as I alluded to before, and of course I don't need the equal sign here, being silly. Sometimes it's hard to talk and code at the same time. You use the from keyword. Okay, pretty intuitive. Now, how do we import Express and makecert? How do we install it to our project? Firstly, I want to say that you can install these globally. What this will do, indirectly, is it's added to your path variable. So you can access these packages directly from your command line, and it'll work. However, I don't always like installing things globally just because it pollutes your operating system. So what I'm going to do here is I'm actually going to install it locally to this project. And in order to do so, you do need a package.json file. Now, the easiest way to do it, of course, is just to type npm in your terminal, followed by init. In other words, initiate a Node project. And it will ask you for certain details. I don't want to be asked for all those details. So I'm going to do -y for just yes. Okay, I'm going to hit return. And you'll see here, this will automatically create a package.json file. Just wait for it. Here we go. Here's our package.json file. It's very simple. What this allows us to do now is install packages, and they will be inserted locally into our project. Now, I don't want to get into a lot of detail on how Node works. I'm assuming you have some basic knowledge of Node. And by the way, I'm assuming you've downloaded Node to your operating system. Otherwise, this all won't work. But anyway, how Node works is that when you access a package, it will default first by looking in your current local directory for a Node modules directory. If it's found in that directory, well, that's the package that will be used. Otherwise, it'll look for global installations in the default global folder for Node packages that you have specified in your path variable. Now, like I mentioned, I want everything local. And this, by the way, will default install a Node modules folder inside our directory here. So let's just clear the terminal. And what I want to do is I want to install, and I'm going to use npm install for this. I want to install those two packages, Express and makecert. That's all I have to do. And if I hit return now, you should see it added to this package.json file. Let me just zoom out. You should see it. Hang on. Done and dusted. We can see the dependencies of our project are Express and makecert. It's been added to our package.json file. And did you notice that we now have a Node modules folder with all the required libraries in order for these, modules, Express and makecert, to work? Very, very interesting. And just to test that your terminal can find those modules, what you can do is type npm ls, short for list, and that will list all the packages locally, right? I can hit return, and you can see here that Node is within our project directory here, local server node API directory, and it can find these libraries, Express and Makecert. Of course, if you want to compartmentalize, is that a word? Compartmentalize? I feel like I haven't quite got it right. If you want to narrow down or hone in on a specific module, you can just type npm ls and we can look. Do we have Makecert? And yes, we do. Okay. Compartmentalize. Anyway, all right. That's clear. Let's get back to our project. Okay, so now we know we've got all of these modules. Let's use them. I want to create our app. If you've done Node and used Express, this is second nature to you, right? I'm just going to put it into a variable called app. And I'm going to now access our Express object and execute it. Pretty simple. What's next? Well, before we get on our keys, and let me say here, create CA keys and certificate, self-signed. And then we're going to have to create server localhost certificate and keys. Before we do that, let's just spin up our server. So now we can actually define a get request. I'll just put your dash simple root, okay? And this is why we use Express. It's just so easy to use. We just have to access our app that we created above, and we can now specify what happens when our server receives a GET request, right? A GET request to which URL? That's right, localhost itself. And then when that happens, we get access to, various objects. One is in a request object, and the other one is in a response object. And then a callback function is executed. Of course, I don't even want to access the request object itself. I just want to access this response and send a message back to the client saying, hello from Node.js server over HTTPS. Oh, it's raining outside. That's good news. We haven't had rain for a long time. We really, really need it. Okay. All right. So now we've defined a very simple route. The next thing, of course, is to spin up our server. So I'll put a comment here, create HTTPS server. Again, I'm going to put that in a variable called server. And now, do you remember we imported this HTTPS module? Well, we can access that HTTPS module now. And on here, there's a method called create server. Now, this takes two arguments. It takes an options argument. Remember, we have to tell the server where our server certificate is and our server private key. We then also have to pass it in our app instance that we created here. Okay, so we could directly put the options object in here like this, but I don't want to. I'm going to define a variable called options and then pass in our app. Very, very simple. Of course, now we have not created this options object, right? We're going to get an error. So why don't we create it? I'm going to put it into a object called options. And to create an option object in JavaScript, you just use curly brackets. Pretty straightforward. And I'll show you soon how we can extract the server key and the server file. So for now, it's just going to be empty. All right. I'm just setting up all of our code. Last but not least, I want to spin up our HTTPS server. Why don't we define a port? So I'm going to define a variable called port, and we can listen on port 4430. All I have to do now is access our server object we created on line 24. On here, there's a method called listen. I want to listen on our port number that we just specified. And when it spins up, why don't we just console log to Node's console a message? And that message can just say server listening on this port number, okay, on localhost effectively. And my dear student, guess what? We are done. Done and dusted. We've set up our boilerplate code. Of course, it won't work now because this options object needs to be defined. In other words, we now need to set up the CA and our server files. As I've already alluded to, I'm going to use this Makecert package. Take a break, buckle up, and let's complete this in the next lecture. Welcome back. Now, as I mentioned, we're going to be using Makecert, and you can see here that its purpose is to generate signed TLS certificates without using OpenSSL. Woohoo! That's what we want, okay? And there are a few ways you can use it. Like I mentioned, you can use a CLI approach, or you can use an API approach. So I'm going to show you both. Let's get cracking. Firstly, let's create our CA keys and certificates. You know what I should do? Why don't I include here a directory called keys, just to keep it consistent with our other projects, our other XCA examples and OpenSSL examples. How do we do this? It's actually very simple. All I'm going to do is I'm going to create an object. I'm going to put that object, we can call it anything we want. I'm just going to call it CA object. I'm now going to use the await keyword. This is very specific to JavaScript. And this allows us to write synchronous code. So it looks like it's being executed line by line. But what it does, that await keyword, is it actually pauses execution of the entire function that follows. So it allows other JavaScript code to run. But when the promise resolves, when that function has produced something, well, then it gets added back onto the stack, the execution stack, and the code within that function then executes. Okay, so that await keyword is quite useful. And then remember at the very top here, we imported two things, create CA and create cert. Well, I want to now access our create CA function. Functions are executed by parentheses. And this function takes an object. Objects in JavaScript are really very similar to JSON in the sense it just consists of key value pairs. So there are a few things we can provide here, and this is specified in the specification of this make cert package. One is organization. We called our CA Wally Warthog Incorporated. Now each key value pair is separated by a comma, and I'll just add a few other key value pairs here. Validity of our certificate can be 365 days. Okay, you with me so far? So now we've created our CA object. We've executed this function. And when we execute this function, the make cert package automatically creates a certificate and a key. How do we access it? Well, we can easily access it. In fact, I actually want to insert those keys and that certificate into files and insert them into our keys directory here. That's exactly why, by the way, I wanted to import the file system module in Node, because I'm wanting to write and access files. Okay, how do we do it? Okay, well, let's just write the certificate and keys to files. I want to access our file system module. On here, there's a method called write file sync, writing to a file. And it takes two arguments. The first is the location of our file, which I can put in our current directory, but in a folder called keys. And then we can call it anything we want. I want to call it CA cert, just to be consistent with all our other examples. And the second argument, of course, is the data we want to write to the file, and that is now accessing our CA object. Remember, that's the object we get returned to us when we execute the create CA function. And on here is a property called cert. It really is this easy. Now I'm just going to copy this down because we're going to do exactly the same thing, but for the key, right? So it's going to be CA key, not in a .crt file, but in a .key file. And I'm not going to access a property called cert. Now I'm going to access a property called, you guessed it, key. And my dear students, we're done. Can you see how easy that is? So intuitive. And we can do pretty much the same thing to now create our server keys and our server certificate. Now, what's nice with MakeCert, we don't have to go through the process of actually creating a certificate signing request. It's kind of just all done automatically. So how does this work? Well, again, I want to execute a function called create cert. Remember, we imported that from the MakeCert library. Okay, so let's do that and put it into an object. I want to define an object called anything we want. I'm just going to call it server object because it's our localhost server here. Again, I'm going to use the await keyword and I'm going to access our function called create cert that we imported, right? It again takes an object. We have to give it certain information. What kind of information? Well, think about it. We need to specify what CA is going to be signing our localhost's certificate. And that's done in a property called CA. Again, now the value here is an object. This object consists of two properties, a key and a certificate. So the key here is a reference to our CA's private key. We know that that CA's private key is on our object here called CA object in a property called key. So it's very simple. I can just literally reference our CA object and access its key. And I can do exactly the same thing for the certificate, CA object.cert. So there you go. That's the one argument we have to provide to this create cert function. What else do we have to give it? What's so important when it comes to a server certificate? That's right, the domains. And that's in a property called domains. Now this is in an array, and an array in JavaScript is represented by square brackets. And here you can literally insert IPs and DNSs that you want your certificate to apply to. So for example, we wanted to apply to 127.0.0.1. And you guessed it, to localhost. We then have to specify a validity period, how long you want the certificate to last. We can just do standard 365 days. Whew, we are almost done. The next step is, of course, I want to write these now to files again. So let's do that quickly. Remember, we have to access our file system module. Here there's a method called write file sync. We're doing exactly the same thing as last time. First, we have to specify where this file is going to be outputted to and the name of the file. So we know it's in a directory called keys, and we called it server cert for the one. And that's going to be assigned the value of our server object certificate, which is put in a property called cert by default by this package. Of course, we can copy paste. We can do exactly the same thing for the key. I want it in a .key file. And I didn't specify a file here, but we want that in a .crt file for our certificate. And that's in a property called .key. Okay. We've got these files. I know I haven't run the code yet. We're going to run that shortly. It's going to be in our keys directory. Finally, we need to now grab them into our options object here. So that's so simple because all we have to do is access our file system module, but now not write to files. We have to read the files. So we access a method called read. You know what? Sorry, I need a property. Objects are on key value pairs. So let's first extract the key. And again, it's in the FS module read file sync method. And you just have to specify where the file is. It's in a directory called keys. And in here, we called it the server key.key file. Object key value pairs always separated by commas. And of course, the other thing we need is not only the key, but the certificate. By the way, those names, key and cert, they are specific to this package. You have to name it as those words, otherwise it won't work. Okay, read file sync. And again, we can grab it from our keys directory, server cert, and a CRT file. And I think this is it. This is all we have to do and it should work. How exciting. Why are we getting an error here? One problem. Oh. Put a semicolon. Sorry. This is an object. Okay. There we go. I think we're all good to go. Should we try and run it? In order to run a node file, how do we do it? That's right. You have to use the node keyword and then you have to specify or tell node which file you want to run. And we want to run a file called app.js, but you don't need to put .js because Node will automatically assume the file it's executing is JavaScript. So I can just write node app, hit return, and if everything works and it doesn't, why? Oh, yes, of course. We're using the import syntax, at the top here, using imports. And in order to do that, we need to specify a type in the package.js file as being modules, ES modules. Of course, I haven't done that, so we're getting a bit of a warning, but everything is working. Can you see our keys directory? Everything was created. Wow, that is so cool. And our server is listening on localhost now 443 over HTTPS. So if I open up a new tab and we type localhost 4430 over HTTPS and I hit return, this is awesome. Yes, of course, we're getting a warning because I haven't uploaded that CA certificate to our operating system, but of course I can proceed to localhost. And would you look at that? We are running. Come on, you got to be happy. Well done. And of course, you can view your certificate, which is really cool. Here it is. Here's our Wally Warthog Incorporated CA. Here's our common name for our local host. Everything is here. Validity period, you can click on details. You can even look at our public key. It's all been done for us. The modulus, you now know what that is, right? Anyway, you know all of that. So well done. I know that was quite a quick way to show you how to use all this. The one disadvantage with this, and if I go to the file structure here, actually, let me just kill my server. Let's just go into package.json quickly, and we can just specify this type here being module. Okay. Now we won't get that error. The one disadvantage with this is that every time we run this code, a new set of certificates are going to be created. Makes sense, right? And I can prove it to you. I'm on the CA cert here. Just look at these end numbers. And I'm going to run our node server again. Let me just clear the terminal. Let's just run it again. Sorry, spelled it incorrectly. Node app. Those numbers are all going to change. You see, I told you so. Of course, now we're not getting errors, which is awesome. But we have a whole new set of certificates. Okay, so how do we get around that? Well, we can implement the second method of using makecert, and that is using our terminal, the CLI. So let's take a break here. And in the next lecture, let me just show you the other way we can use makecert. It really is quick. And we are almost done, so stick with me. Adios. Welcome back. Such a bittersweet moment for me, because I know we're kind of getting to the end. But I hope you have learned a lot. I really, really do. And thank you so much for your support. I love you tons. I couldn't do this without you. And I love doing it. All right. So quickly, let's now look at using the CLI. Now, there is a slight nuance here. And I'm going to show you that shortly. All I've done is I've now created a new directory called localhost server node _CLI. Okay. Firstly, we don't need to import anything from make cert. Okay, so I can delete that, and we can delete all of our keys here. Let me delete. So now we've got an empty keys directory, and we don't need anything in our code. I can delete our object here. I know, weird. We don't need the file system module anymore. We don't need the server object. So I'm just going to highlight everything here. You know what? Let me just collapse this terminal. There we go. How's that? I think that's it. Look how streamlined our code is. We are going to need this option still, because remember, we are creating an HTTPS server, and I am going to have to create a server key and a server cert file. That's our goal. But now I'm just going to be using the CLI. Okay, so there is a slight nuance now, and that is make cert is not designed for us to start now typing in the terminal. For example, I can't now type make cert. It's not going to work. You might be thinking, why is it not working? We've installed it. It's in our node modules directory here, and it should be here, right? Make cert. There it is. Just realize, yes, we have installed make cert locally in our project within our node modules folder, but you're still not able to run it directly in your terminal because it's not a global path variable. Basically, your shell doesn't understand what make cert means. So how do we get around this? How do we ensure that our terminal knows what make cert is and we can start using its functions? There are a few ways. Most developers, and if you actually go onto this npm package website here, you can see here at the top, they're telling you, hey, you need to install it globally. But as I mentioned previously, I don't really like polluting my global packages for npm. It can soon get out of hand and very, very large. But you can do it that way, okay? I'm just going to use, instead of typing npm, I'm going to type npx. What this does is it will install the package temporarily, do its thing, and then when it's done, it will remove it. So it's great for one-off tasks, right? And that's exactly what I want here. I want to create our CA certificate and keys, our server certificate and keys once off. After which, hey, I don't need make cert anymore. So I'm going to use npx. Okay, let me just collapse this quickly. And how does make cert work? Well, remember with OpenSSL, you had to specify we want to use that library. It's the same with make cert, so we have to specify that we're wanting to use the make cert library. Let me just zoom in here so you can see better. Is that better? I hope so. I then want to access its command called create CA, and I have to tell the make cert library where I want these files to be outputted to. What files? Well, the key file to start off with, and that can be in a directory, in our keys directory, which is in the current directory represented by // in our keys directory, and I want to put that in a file called ca keys.key, and I want to do exactly the same thing for the certificate. It's going to be in the current directory in our keys folder, and I'm going to call it ca cert.crt. You got to admit that is pretty easy, and if I hit return, everything should run as expected. Oh, unknown option key. I've used one dash. Sorry, I've got to use two dashes. Finicky. Isn't this finicky? Let me hit return. What do you know? No errors. If I open up our folder directory here and we go in our keys folder, there it is. There's our certificate and there's our key. Wow. Can you see how easy it is? Very, very easy. Let's just clear our terminal. It's getting a bit messy. Now that we have our CA out the way, we can now generate everything we need in order to successfully run our node server over HTTPS. We have to produce those two server files. So again, npx, I want to run the make cert package. It's not going to be create CA now. It's going to be create cert. I now have to give this package the CA that's going to be signing this certificate. So that's done in a flag called CA key. And I just have to point now to the file that we put that key in. We know it's in the current directory, in the keys folder, in a file called ca key.key. I have to do exactly the same now for the certificate. It's in the current directory, in the keys folder, in a file called ca cert.crt. Last but not least, we have to tell this package where to put the server certificate and the server key. Again, --key tells the package where to insert the server key. I want it in the current directory in the keys folder in a file called serverkey.key. And the same thing with cert, right? Current directory, keys, server cert.crt. You have a hit return, we should be done and dusted. Unable to find CA key or certificate. Why? Oh, I spelled it wrong. I spelled it CA key.key. You know what? I actually shouldn't have done it .keys. That was my mistake. It should be a singular. Now if we run this code again, it should work. Let's try it. Pat yourself on the back and everything should work. Of course, we should be able to now run our Node project. Server's listening on the port. No errors thus far. We can just type HTTPS localhost 4330 and everything is working as expected. We can proceed. Well done. Seriously, seriously well done. You now know so many different ways to create keys and certificates, and you can see after a while it just becomes mundane. But it's so important to grasp fundamentally what it is you're doing, because then you can tackle anything that's thrown at you. So well done. I'm super proud of you, and I'll see you in the next lecture. Wait. I just thought, I didn't actually explain to you why is this working over localhost, because we didn't specify domains. And the reason is by default, the makecert package puts 127.0.0.1 as a default domain. Actually, it should be here on their website, yeah? There. See, by default, it's set to localhost, a DNS of localhost, and an IP of 127.0.0.1. But you can change it, right? You know how we put our options here? CA key, CA cert. We left out validity. We just used all the defaults. But you could insert your own domains by just typing -- domains and then inserting them after that, okay? Very, very simple. So there you go. Enough said, let's move on. Hey, well done for completing the course. And like I always say, it's a bittersweet. I love going through the courses with you. I love producing the content. It really has taken me many years to gain all of this knowledge. And seriously, I spend a lot of time thinking about what is the best way to structure a course to benefit you the most, to make you a Grandmaster developer. Because hey, let me be honest as well, I know you've got a lot of options. So I really appreciate the fact that you trusted me, that you enrolled in this course, and well done for sticking with me to the bitter end. You now know a lot more than 99% of other developers. You now know how TLS works. Where to next? Well, the world's your oyster. Keep coding, keep developing. What's that? Hello, SWAT team. It's the SWAT team. What? Your website has just been infiltrated? Well, why don't you do my course, TLS HTTPS? Yeah, do it right now. What? You want another course as well? Alright, SWAT team, I'm on it. Thank you so much, and I'll see you in a future course.